Thanks for coming. Really, I appreciate y'all being here a lot. This is something that I've been excited about for a long time, but haven't quite known how to give a lecture on, and I'm finally trying it. It's a long-standing project for me, so I know that most of you, well, you've all graduated, and for most of you, like this was something for you to come out for, and I appreciate you coming out. I really do. So this talk is called "How Do Computers Even?" And it's about simulating the Nintendo in JavaScript. I estimate, so it's actually not 3,000 lines of JavaScript. It's, I think, 1,400 now. It'll be 3,000 when the graphics and audio are working. Spoilers. But we won't be covering that today anyway, because there's a lot to talk about before we even get to audio and graphics. Another title for this talk is How to Spend Hella Time on a Project That Can't Possibly Make Money, which is an alternate title. A long time ago, I spent a decent amount of time playing Nintendo games. One in particular, I played a lot of Mega Man 2, really a lot. I don't know why it hooked me in particular, as opposed to Zelda or Super Mario Brothers, but that worked for me, and I spent a lot of my childhood in the year 20XX. And on a larger scale, video games were kind of the first thing that really enchanted me about computers. It was the first chance that I saw a complex system that I could interact with, and it would respond immediately, and I could see what would happen. And the feedback loop was really quick, right? You press a button, something happens, you observe the effect on the world, and you kind of repeat that. And that was, from a very early age, that was pretty enticing. In 2007 to 2011, 15 years later, I wasn't the most disciplined person, like going through college, those sorts of things, but I needed to figure out what I was going to do for a career. And I was studying economics and literature at a liberal arts school and was very confident I didn't want to do that for a career. And I thought, what is something that I just can't get bored of? A lot of things, you couldn't make me do them because I would just feel like, I don't care, that's not interesting. And I would just piss off because I was a brat. And so I was trying to think of what I could get into that wouldn't lose my interest. And I got into programming because I wanted to know how computers work. I mean, really, what are they doing? How does it work? How does the whole thing fit together? And that was sort of endlessly fascinating to me. And in a lot of ways, it still is. And I feel like there's still a lot that, I don't know, but that's okay. So in 2007, I left liberal arts school. I self-studied SICP, which people have probably heard me talk about before, the Structure and Interpretation of Computer Programs, this book that they used for the freshman course at MIT for the better part of 2 decades, that I'm a huge, huge fan of. There used to be a copy floating around the campus somewhere. I'm not sure where it is these days. I have another copy at home. Basically, if there is a programming Bible, I think it's that. I spent a bit of time studying that book. I wrote a lot of Lisp, both Scheme and a language called Common Lisp, and then I graduated. I got my first CS degree and my first job, and that was awesome. That was a big success for me, and a confirmation that this was something that I was interested in and something that could support me, because I was so interested in it. But I still didn't know how the Nintendo worked. I mean, I could write programs, and I could build web servers, and I could do all kinds of stuff, but I didn't know how the Nintendo worked. That was still kind of magical. And that seemed really stupid because a Nintendo is very simple. It's not a powerful machine. It's not a complex machine, right? It's old 80s hardware. And I think that was something that kind of bothered me. I had that first job. It was 2011. I'd been there a while. I was feeling comfortable about how I was doing there, but I still had these sort of unresolved questions about what was happening at a low level in computers. And that's kind of a pet issue for me. I think, these days software is incredibly powerful. It's incredibly complex. Computers are the best they've ever been. I think we can hopefully all agree computers are the best they've ever been, but even as programmers, below a certain level of detail, we just say, it works and that's fine. Right? And that's we have to. I mean, nobody knows how a 747 works all the way through either. And you may have heard me use that analogy in class before. But that's kind of a pet issue of mine. That's something that I'm concerned with because I think at a certain point you stop striving to make software perfectly clear and you stop stating your assumptions. At a certain point you start writing code on the job and just go, well, this works. That's fine. And not treat the code as a pedagogical tool or something that really should be a pretty firm but clear description of a process that a human could do by hand. And our software no longer resembles that at all. There's a time when that was a goal for software, and that time is gone. Personally, I've had to make peace with that, right? Like, industry is not going to change. Industry is not going to suddenly start trying to write all software to teach people how the business works, and that's okay, but that's still something that I think about a lot. And so these low-level foundations beneath our frameworks and our libraries are like, they're kind of these fuzzy mysteries that are, mostly forgotten. And I think that's probably why I'm really into Smalltalk and Lisp, these old languages from like the 70s and the 80s, is because they date from a time when programming languages and programming environments had different goals, when it was something to aspire to. Somewhere Dan Ingalls has written down a list of like desiderata for the Smalltalk programming language, like what do we set out to do in making this programming language. And one of the very first things in there, this is so that these pet issue things linked to blog posts and talks I've previously given. Where is it? One of the things Dan Ingalls says, which I really love, is personal mastery. If a system is to serve the creative spirit, it must be entirely comprehensible to a single individual. I guarantee you no programming language written past 1990 has that as a goal. I just promise you that people are like, it's not happening anymore. And that's okay, but that's something that I have a lot of feelings about. Anyway, this is an old talk I gave. You can read it from the link later if you want. The thesis is the age of comprehensible computing is over. Like, we don't care. That's not a problem anymore. But it was still a personal issue for me. And so I think in 2011, that's what really motivated me to just say, you know what, I'm just going to sit down and simulate this thing and try and figure out what it's doing. And try and do it in a way where, like, the result is something I can give to people and they'll understand it, right? So, like, I had this personal quandary, like, I really have this problem, like, what am I going to do about it, right? Nobody cares about the foundations of computing, including us most of the time, and that's okay, the world's going to keep on doing that, but, like, if I care about this, what can I do? And these are two quotes I really love. First is by Alan Perlis. You think you know when you can learn, you're more sure when you can write, even more when you can teach, but you are certain when you can program. If you can teach a stupid computer how to do it, you know how it works. You've got a pretty good idea of what's going on there, right? So if you want to know how the low-level foundations work, build the low-level foundations with code. You will know how they work, right? And two, again, one of my favorite quotes in the world, thus programs must be written for people to read and only incidentally for machines to execute. I took those two quotes and I thought, you know what I should be able to do? I should be able to make some piece of code that describes the low-level behavior of the Nintendo in clear enough terms that I could hand it to somebody that had basic knowledge of programming but not extensive knowledge, and they could kind of piece it together and go, okay, I think I see what's going on here. And to me, that's a noble goal. To me, honestly, for whatever reason, that's like shoot for the moon, like go there, do it. And so that I started in 2011. I had this goal, like I know that computers can simulate anything that we can describe for them, any consistent series system of rules, and that includes another computer, right? There's no reason you can't have one computer simulate another computer. That's perfectly fine. You just have to be able to describe how it works well enough. And I wanted to understand how these things worked better, so I set out to simulate a Nintendo so that I could play Mega Man 2, because it's the best. An unstated thesis of this is that Mega Man 2 is possibly the greatest game ever made. I'll just take it that you all tacitly and agree with that assumption. So the rest of this talk is going to just walk you through all the stuff I've encountered so far. This has kind of been an on and off project or series of projects. I've written like 5 or 6 different libraries or programs that kind of go in different directions with this over the last 3 years. So like this is kind of a jumble of like different stuff that I've encountered. I'll try not to get too lost in the weeds. Please do ask questions when there's something that you're excited about, that you're curious about, that you're like, no, tell me more. Like we can't go past that right now. I want to answer questions where I can. So in 2011, I undertook this thing. I started writing one in Common Lisp because I loved Lisp, and that just seemed like the right thing to do. And I tried to make it, like I said, I really wanted readability as a goal, and so I actually had it so that you could go into the source directory, which I have lying around here somewhere. I had it so that you could actually go into the source code directory for the project and type make book And that would invoke a shell script that would generate a PDF of the source code with annotation. And in fact, I then took that PDF and put it up on Lulu and wrote a blog post about it. And I didn't get that many sales, but I made like $5 off of it. So you can make some money. As evidence, here is the book in question. If anyone would like to have a gander after this presentation, please do. It's called CL6502, a readable CPU emulator. But long story short, what gets generated by the make book script is a PDF that has some attribution rights. These are all the different people that were involved in the code for this project, ordered by number of lines contributed. Justin, Big Ed, and Batesel are different people that I worked with that contributed, like, hey, you should put the GPL license in there. Hey, you should, like, very, very, very minor comments that they just kind of offhand, like, jokingly made. And then I was said, well, write a commit, send me a pull request. And they did. Dustin is a guy in New York who decided he wanted to write a Nintendo game, like an actual game, in 2012. And he wanted to be able to unit test his code. And he didn't really know how to do that. And so he decided to use CL6502 for some reason. I don't know why. And he later shipped the game. There's actually a YouTube video somewhere of, like, there are cartridges. You can buy physical cartridges that have his game that he made in 2012 for the Nintendo that he unit tested using my CPU emulator. So that's really weird. But he contributed probably 500, 700 lines of code. He gave me an assembler. I had an assembler already to compile code, basically. But it wasn't very good. He made some really nice improvements and sent me some contributions. But long story short, what's in this thing is a table of contents and then sort of all the code is broken up into chapters, and it literally walks you through the code. So it starts by saying, like, okay, here's an introduction, here's some stuff about, like, what is this project, like, what are our explicit goals, what are we trying to do, what about performance, why Lisp, like, all this kind of stuff. And then says, okay, well, like, let's start diving into the code. Here's the first thing we'll look at, give a little bit of introduction into what that is and why it's there, and then, like, here's the code, and try to make the code as readable and reasonable as it possibly can be, and then move on to the next chapter, that sort of thing. So I put that together, and that was kind of cool because it's generated from these markdown files. You might notice in the source directory, like, there will be an addressing .lisp file, which has the code for addressing. And there are a couple comments in there like this that get put into the book as headings. But then there's also an addressing.markdown file, which is kind of these chapter introductions. And it just, the script just puts all that stuff together and gives you a PDF, which is, like, super fun to play with that and have this sort of different product than what we normally think of code as being for, right? So that's this thing I did in 2011. As you can see, I got to a point where a video was doing things. But I sort of stalled out in 2013 from a mixture of, like, boredom, like, I'd been looking at the project on and off for a while, and also life changes. I started dating Norma, I got a new job, like, I just had a lot going on. But I also made some crucial false assumptions that I'd gotten stalled out on about how the Nintendo worked, and that is the death of so many programs. You will get killed every time being like, well, I'll write it this way for now, because that seems like it's how it works, it's fine. And then later, like, oh, no, that's not how that works at all. There's actually a really good Fred Brooks quote about this, which is, the management question, therefore, is not whether to build a pilot system and throw it away. You will do that. Hence, plan to throw one away from the beginning. You will anyhow, right? Sometimes this is referred to as build one to throw away and build one to keep, right? Write a prototype, then try and write the actual thing. In my case, I ran into a lot of issues because, like, I was learning this thing as I went, just like we all do when we program, and I didn't really understand a lot of things. More recently, I've got this thing called Nescavation, which is running in a tab right here. It's a browser-based effort, right? It's in JavaScript, which solves my deployment problem. I was really unsure how to send a common Lisp program to people running Windows somewhere else on the world. That was not going to be fun. So this solves that issue really nicely. But anyway, I've been working on this for about 3 or 4 weeks now. The graphics aren't there yet, but considering that it only took 4 weeks to get where I am, I feel good about that, because last time it took about a year to get to this point. Also, it helps that I know a lot more than I did the first time around. And I'm doing it just because, you know, lifestyle down, I'm still really curious about this, and I can make better assumptions about how things work than I could last time. Okay, so to simulate a Nintendo, obviously we have to simulate the different parts inside the Nintendo. And in case you haven't opened up a computer or built one in a while, a couple of those parts that we really care about are the CPU, right, where all the work, all the real kind of work is done, or at least most of it. The memory, where all the data is stored. The video card and the sound card, which self-evident, I hope. Controllers, and finally cartridges, right? In terms of the Nintendo, we have to simulate the cartridges. Thing didn't have a hard drive, didn't have some type of permanent storage. The only permanent storage there was those cartridges. So I started with the CPU in 2011, and for similar reasons, I'll start with the CPU today. It's the brain of the machine. Until you've got that part working, you can't really do the other pieces. And it also seemed kind of simpler than the graphics and sound, neither of which I really knew anything about then, and which I only kind of understand now. Okay, let's talk about it. The MOS 6502. So the 6502, for those who have heard those numbers a few times and are not sure, is the name of the CPU chip that was inside the original Nintendo. Okay, questions before I go forward. How are we doing out there? Having fun? People? Yeah, Ben.
Which is your favorite one so far?
Between the Lisp and the JavaScript? I don't know if I have a favorite. I like the design better in the JavaScript one because I know what I'm doing more. Like, I just think the Lisp version's very pretty, and I will never stop loving. Like, I have this one macro I wrote to define all the opcodes that I just think is beautiful. Like, I just love this macro. I'll pull it up right quick. Whoops. This thing. This piece of code, while it might look terrifying to y'all, I'm very, very happy with and very kind of proud of in a way. This thing wound up being so nice because what it actually does, which we'll get to a little later to see how I did in JavaScript, is it takes a very short snippet of code like this top one, LSR, and it defines 5 different methods that are stored in different places in an array with different settings and like mostly the same but slightly different behavior. So it actually, like, that macro is so wonderful, and like that thing wound up being really awesome. I wouldn't say I have a favorite between the two versions, but I'm still very partial to certain things I did in the Lisp version just because of all the time I spent with Lisp. The better design is the more recent one, from my perspective.
Just to be clear, we will not be playing Mega Man 2 today.
Unfortunately, we will not be playing Mega Man 2 today. I apologize for that. I'm disappointed about that too. And if you really want, I mean, we could do something like. Oh wait, there we go. Right? Does this help? Does this slightly ease the pain? For those who don't know, this was a substantial portion of my childhood. Yes. Like, very substantial. No. Good question. No comment. Yeah, it's good. Okay. Other questions? Cool. Okay, so the CPU. So conceptually, 8-bit CPUs are actually pretty straightforward. They're not that, right? The CPU is not that powerful, and it's not that complicated. It's not that bad. This totally changed in the 90s. Things when Intel took over and Pentiums came out, and then we started having L1 cache and L2 cache and like a memory hierarchy to deal with, and then multiple cores came into the picture, and so you had to think about like synchronization between cores if you want to write multi-threaded programs. Like, holy shit, this stuff got bananas in the 90s and 2000s. It is real hard to figure out what a CPU does these days and think about how to simulate it even kind of correctly, because there are 4 billion transistors in a modern CPU. Good luck finding an engineer who can explain all the ins and outs to you, like a CPU engineer. But in the 80s, it wasn't that bad. You had the MOS 6502, I think it's like 15, 20,000 transistors, something like that. Like, it's not that big. You probably could find a printout of the die that was big enough that you could figure out most of what was going on, if you had to. Though I don't know any electrical engineering, so I couldn't do that. So here's what I've learned about CPUs. All CPUs, they know a certain set of instructions. Those are just commands that are built into the CPU that it knows how to do. It's native language, right? That's commonly called an instruction set architecture, or ISA. A CPU has to have access to memory, otherwise it's not very useful, right? If it doesn't have access to memory and there's not some kind of I/O with like keyboard or controllers, and there's not some kind of video output, then you can turn it on and it will create heat, but what does it really do? No one knows. But so it has to have access to memory, and then CPUs have a few registers. So registers are tiny, tiny boxes of storage. I'm talking variables that are either a single character or a single number. Like that's what we're dealing with. You don't have arrays, you don't have hash tables or anything like that, dictionaries. You've got registers. They can hold a number. It's kind of what you have. And then they have one special register. They have a number of special registers, but one very special register called the program counter. So the program counter, when you're running a CPU, all it knows to do is go to a certain place in memory, look for an instruction, and then run it. And so the program counter is what says where in memory to go to get the next instruction. It is literally a pointer to the command, the method or the command you're running right this moment, or the CPU instruction, really, right? So that's very, very important. So that's the program counter. And what a CPU does when you turn it on is it literally just reads the memory from the program. So it looks at the program counter, which specifies some address in memory, right? So like 6014. It goes and looks in memory at 6014 and sees what's in there. It should be some kind of instruction. The CPU says, oh, which instruction is this? It gets the instruction and it like runs it. So it says, oh, this is an add instruction. Fine, I'm going to do an addition. That instruction, when it's run, will change the program counter, and the program counter should then point to the next instruction. And the CPU says, fine, okay, now I'm going to run this instruction. And it just does that forever in a loop. So conceptually, that's not that bad, right? That you mean like we can just write while CPU is on, like get the next instruction, and then just like run it? Like this is easy. This is totally fine, right? Yeah, like not quite. But that's a nice thought. So let's deviate for a moment to kind of walk you into this. For some reason, I thought the next best thing to do would be to just look at some assembly code right away. So we're going to do that. I've never given this lecture before, so this is an experiment. Have fun. Okay, so wait. Okay, fine, yeah. So you program CPUs in assembly language. Assembly language is just text. Assembly language is just text, but you feed that into a program called an assembler that reads the text and winds up spitting out machine code, which literally is just a binary blob of numbers. It's just a big array of numbers, right? It's a file that's just a big array of numbers. And then that is what gets loaded into memory, and somehow the CPU picks an instruction to start with. We'll talk about that in a bit, but it picks the program counter starts somewhere in that blob, and then it starts going, right? It runs. So there are a couple things that I want us to really get up front to think about before we dive into the assembly code, just to things that are assumptions that we have from normal programming that just don't hold anymore. So one of those is that there's not an operating system. If you're doing assembly programming, there is no operating system underneath you to do any of the things that an operating system normally does. So the two biggest things, from my perspective, that an operating system does, at least if you go back to like the 70s when they first came out, is one, they give us some standard way to interact with hardware so that if you want to use a keyboard, you don't have to write a keyboard driver. If you want to use a video card, you don't have to write a video card driver in your code, right? The operating system does it. Right, so that's one thing. The other thing is they allow for multitasking, right? That actually wasn't always the case, but it's very quickly become very important to us that the operating systems allow us to run multiple programs at the same time. We don't worry about those programs breaking each other's memory. If Chrome crashes, normally it doesn't bring down Adobe Photoshop, right? That would be really bad. So like there's some sort of process isolation that we get from operating systems that we like a lot. That stuff does not exist in assembly code. Right? In assembly code, you control the hardware. That's generally done by working with certain regions of memory. And this is the only point of these that's slightly particular, the 80s, and assembly programming in the 80s on like 8-bit microcomputers like the Nintendo. But long story short, certain regions of memory will actually be wired up directly to the hardware. And if you read the hardware specifications, like what does the video card do? What does the sound card do? They say, hey, if you send these instructions to the hardware, which is at these places in memory, certain things will happen, right? Okay, so one, there's no operating system. Everybody cool with that? Two, there's no garbage collection. This is, and if you've written C or C++, that won't seem weird to you. If you haven't written C or C++, here's the big deal with that. You don't really have variables. You can't just say like, oh, you know what, and I want to var x, and I'm going to put 42 in x. You can't do it. You have to say, I want to put 42 in this place in memory, or I want to put 42 into the CPU register. And then you have to remember, like, ooh, later, if I want to get x, I have to go to that place in memory. Right? You don't have variables, not in the same way. You have addresses and registers. Finally, two more things. There are no data types, so that means that everything is just a byte. There aren't even really numbers. This is kind of a small distinction to make, but at the level of the CPU and at the level of memory, everything is, certainly at the assembly level, everything is being stored as just a byte in memory somewhere. And a byte can have 255 values, right? It's between 0 and 255, and we'll talk a little bit more about that in a minute. So 256 possible values ranging from 0 to 255. Yeah, but so, you don't have higher level data structures in the same way. You can represent things, you can choose to lay out stuff in memory however you want if you want to organize your bytes, but ultimately to the CPU and to the assembly language, it's just a bunch of bytes that are at different addresses. Okay, and I say we don't even have numbers because normally if you hear the word, I don't think if you're doing assembly program that you should if you're doing assembly programming that you should think you have numbers, and I'll talk more about that in a minute. Finally, there aren't functions. There are not functions in assembly code. You do have branches for if statements. You do have jumps and jump subroutines and things like that for going to a different place in the code. Right? But you basically can say, go to this address in memory now. You have instructions that let you say the program counter should next go here. Right? So you have the ability to tell the CPU to go somewhere else, but you don't really have a function in quite the same way. Okay. So I'd love for us to talk about what you do have. Before that, are there questions about anything on this slide? This is kind of heavy. Questions? Thoughts?
So when you were talking about like everything, when we do have an operating system, everything has its own place in memory already, the hardware stuff.
Yeah.
Is that what's like the kernel memory? Is that what that's like stored in, or like?
So as far as how operating systems normally mediate access to hardware, it depends on the operating system. In terms of modern operating systems, Linux, Mac OS, Windows. There are a set of libraries that ship, so the kernel directly manages all the memory, but every process has what's called virtual memory. So every process thinks it literally owns all of memory. It doesn't, but the OS kind of lies to the process, and the interface, the API that you have through the operating system libraries lets you store stuff in memory, but it doesn't really let you, and it'll give you the address, but it will give you a virtual address, and then whenever you say, get me the thing there, the CPU maps that to your real memory to figure out kind of. It gets complicated. We can't go into that. That's like take an operating systems course. I haven't.
Like how often is the program counter incremented, and is it just endless?
Yes, the program counter is incrementing basically endlessly and many, many times a second, however many instructions you get through, which varies. But you can assume many thousands of times a second.
But it's equal to the amount of instructions. Is that fair to say?
The program counter is always pointing to the next instruction to run. It will run many, many times a second based on the speed of the CPU in megahertz or what have you.
So even though it's a counter, it's not actually counting, it's a pointer.
It's a pointer, yeah. It's called the program counter, but it's much more accurately a pointer to memory. There's not a thing in the CPU that says how many instructions have been run. If you're doing an emulator, you do need something like that. Yeah, Will.
How many lines of code in assembly language did this take that, does JavaScript reduce the amount of code?
Any higher level programming language than assembly wildly reduces the amount of code to do something. Well, generally, yes, it's going to take more lines of code to do it in a lower level language. That's not 120% accurate, but I mean, there are scenarios where low level actually, if you're solving a low level problem, it's possible that low level abstractions are going to be the most suitable ones to do the work. But in general, for Super Mario Brothers, for example, I have the original, well, I don't have the original source code to Super Mario Brothers, but one thing that I've come into during my time researching all this stuff is someone who meticulously reverse engineered and then rewrote the entire source code to Super Mario Brothers such that you could feed his file with comments and like variable, like constant names and stuff like that into an assembler and get a bit identical copy of Mario back. So I don't have that kind of time yet, but we'll see. And that thing, where is that? No, it's in the tests, isn't it? No, it's not in there. Oh, I know where it is. Hang on. Sorry. So Super Mario Brothers, I'm actually kind of interested by the question too. The question was sort of, is that a test? No, it's not a test. Where the hell did I put it? Yeah. 16,000 lines of code for the code to Super Mario Brothers. We don't have any JavaScript to compare it with. I expect if we did, it would be less. That's the best I can say there.
Okay. So you're estimating yours to come out at around 3,000?
That's to simulate the Nintendo.
Okay.
I don't have
Okay.
so I don't know. But in general, assembly code is verbose, yes.
And number 3, that's because we're dealing with an 8-bit processor.
Yeah, and I'll talk more about that in a few. Okay, so what do we have would hopefully be the next question. Like, okay, we don't have garbage collection, data types, functions, or an operating system. Like, what the hell do we have? So you have the MOS 6502, which is a historic CPU. It's actually really cool. It played a huge role in the microcomputer boom of the 80s. It was in the Apple II, the Commodore 64, the Nintendo, and the BBC Micro. So it basically was in every major home computer of the 1980s, which is bananas. Like, this thing sold a lot of units, and it was a big deal. Fictionally, if you watch the first Terminator movie, at some point you see his vision, and there is 6502 assembly code scrolling in the side of the screen. There is a Futurama episode where they have a screenshot of Bender's head with like a zoomed-in X-ray thing, and it shows a 6502 in there. I don't think a 6502 could possibly ever power a robot, but it's still a cute tribute, and I like it.
He's an assembler.
That's true. Okay, so what do you have? Well, you've got a 16-bit program counter. So the program counter is actually 16 bits, meaning the highest number the Nintendo can talk about, the highest number that the Nintendo can count to, quite literally, is 65,535. Right? So it can represent numbers from 0 to 65,535, meaning that so it says there, meaning it can address at most 64 kilobytes of memory. That's slightly inaccurate. The most accurate way to say that is the Nintendo has a 64K address space. It has a 64 kilobyte range of addresses it can speak about, because that's the biggest number it can say, if you will, at one time. Yeah. And if you don't have a CS degree or you're not fluent in binary, don't worry, we're going to look at that some more in just a minute. Okay, so it has a 16-bit program counter. It also has three 8-bit registers. They're kind of general purpose. So it has an accumulator register, which is the most general purpose of all registers, and then an X and a Y register. So those are all three registers that just, you can store a byte in them. Who knows what you might want to use that byte for? But everything in a computer is bytes, right? So you've got three general purpose registers. In addition to that, you have a stack pointer. The stack, it was very common to have some sort of like stack-like data structure in low-level computing, and we'll talk about that maybe at some point. But basically, you have a register that points to a region of memory that is generally one page. A page is considered to be 255 bytes for the purposes of this. 256 bytes. So 256 bytes makes up a page, and the stack pointer tells you in that region of memory called the stack, where is the top, basically. Where are you currently on the stack? So it just is holding an address for that. Finally, you have an 8-bit status register. The status register is used a lot. It seems a little bit weird to us probably, and I don't actually have a ton in the slides about this, but I know it seemed weird to me initially. The status register actually is representing what's called a bit field. So this is a thing I didn't know about that's very common in low-level programming. Bit fields are basically a way to say, I'm going to have a number, but I'm not actually interested in the number. I'm interested in all the bits inside the number. Each bit will tell me a specific thing is something true or false. So we'll look at that more in a little bit, but long story short, the status register in the Nintendo was a bit field that basically told you, like, if you just did an addition operation, was the result positive or negative? Was the result possibly bigger than 255? Things like that. It just stores some true-false information for us about those kinds of things. And that's everything you had. That's the whole thing. So on the one hand, like, that's kind of nice. There's not a whole lot there, you know? There's not a whole lot that we'd have to model from a data structure side. Now we'll look at some code. This is actually the boot code for Super Mario Bros. 1, which is apparently not the easiest game to start emulating. I didn't know that, but apparently it relies on a lot of very specific hardware behavior, and you're better off trying to start testing your emulator with, like, Donkey Kong or Mega Man 1. Anyway, here's the boot code. So I'm going to try to walk through this as best I can. On the left, you'll see some, and don't worry about getting all the details of this. We're just going to skim it quickly for flavor, okay? This is for flavor, not for perfect retention. So on the left, this is written in assembler. So you've got some, these are called labels, like start : v blank 1 : v blank 2 : wboot check : This is how people kind of faked having something like a function. It's not a function, but you have a name for something, and if you use that name, it refers back to the address where that thing is. So if we look at this, the first thing it says is an instruction called SEI that stands for set interrupts to be enabled. Interrupts in hardware are a way for it to have the CPU stop in between instructions and go do something else and come back later. Like maybe it gets an emergency message from the controller that's like, they pressed left, you got to do something, you know, and it's got to go process that input. The controller might trigger an interrupt. The CPU would go to wherever the interrupt handler is defined as, deal with that, and then go back. Right? So first they say, the first thing they say in Mario is like, turn interrupts on, because we need that, right? We want that to be around. Second, they say clear decimal mode. That's what the CLD instruction is. It's clear decimal mode. Decimal mode was this thing they had in the early or in the 6502 processor for people who didn't want to add in binary. It was more expensive to license and actually like kind of complex circuitry. And so the people building the Nintendo in Japan were like, yeah, you know, we don't need to do that. We don't need decimal mode. And it will save us money if we don't have it. What's the cheapest way we can take it out? And they actually left it on the chip, but just like sliced the lines that actually go to that functionality. Like they just cut the wires, basically. So technically you don't need to clear decimal mode on the Nintendo because if you turn it on, it won't work. But in practice, everybody starts their 6502 programs for the Nintendo by saying, hey, I want interrupts to be on so I can go do other things suddenly. And I don't want to use decimal mode anywhere. I guess it's just for readability from their perspective. That another programmer could be like, oh, this is for Nintendo, so we don't have decimal. I mean, I don't know. Anyway, that's a thing. Josh.
Question.
Yeah.
Okay, so you said that the start colon is a way to kind of emulate a function.
Kinda.
So the start is in memory somewhere.
Somewhere.
And then those are specific instructions that are written within that memory.
Yes.
block.
Yes.
Okay, so when the CPU starts, or when the game is entered, or whatever, is the program counter at SEI, and then when
Yes.
that's done, program counter goes to CLD,
Absolutely.
and then when it gets through to
XS.
TXS, then it's saying, okay, so go to VB blank 1?
Kind of. I'm going to talk more about that, but yes.
Kind of?
Yes. So, okay. So going through this code a little bit faster now. LDA is a load instruction. That's loading some value into the accumulator. STA is a store instruction. That's writing some value out to memory. LDX is loading to the X register. TXS says take whatever's in the X register and put it into the stack pointer. So move the stack pointer, basically. Reset the stack pointer. So what this code is doing is just some basic setup. And it's loading something into the accumulator, which it sends out to the video card to basically tell the video card, turn on, we got to do some stuff. Then this is where it gets a little bit interesting, and this is the big reason that I put this slide in here. Well, one reason I put this slide in here. So Josh is correct in that the way that this works is when this code is, when the Nintendo starts up, the program counter inside the Nintendo is pointed at start, for lack of better terminology. The program counter is pointing directly at this SEI instruction. When it runs, after the SEI instruction, it bumps just by 1, just to the next line, basically. So it bumps the count by 1. That puts it to CLD. CLD runs. That bumps the count by 1. It runs load accumulator. Load accumulator runs. It bumps by 2. Anybody know why? What's different about this line than the two above it?
The first bump tells it where to go to read that instruction, and then the next one tells it to go to the next instruction.
So the second bump is there because we need to skip over this argument. This is an argument to the load accumulator, and it's stored in memory right next to it. So in memory, the way that this is laid out, if it was an array, was first number is SEI, second number is CLD, third number is LDA, fourth number is whatever this is, fifth number is STA. So for the CPU to work, you've got to be able to bump the program counter by however much space the arguments for the instruction are. Did that make sense? A little bit? Head swimming, but like a little bit?
So the CPU has to check what the instruction is in order to know where to go to next.
The CPU actually had hardware that said, like, based on this instruction, this is how much the program counter moves by. Yeah. We have to emulate that.
Right.
But yeah, the CPU did it automatically. So it does keep going, as Josh says, until it reaches this line, at which point, when it's on this LDA instruction, the program counter is v blank 1, whatever that value is. Now this line says, I want to pull some information from the video card. So specifically what it's doing is it's pulling some information from the video card and storing it into the accumulator register. And then this is a branch instruction. This says if the data that came back from the video card is positive, go to v blank 1. Otherwise, go to the next instruction. So this is our first conditional right here. So this is ultimately a while loop. What this thing basically says is, so the PPU status, the thing that they're checking, which I can explain the details of later, but it goes into a whole bunch of stuff that's kind of fiddly, that's not super important. If the video card has rendered a frame, if the video card has rendered a frame, then when you read that memory address, PPU status, when you read from there, the value you get back will be negative. There's a period in between frames. So the video card renders a frame 60 times a second, right? There's a period in between when one frame ends and the next frame begins, and that period is generally called v blank or vertical blank. So what's going on here is they're saying, we want to give the video card some time to start up, so we're going to load from memory from this particular place, and as long as the result's positive, a frame hasn't happened yet. So we're going to keep waiting, right? It hasn't rendered out a frame yet, so we'll keep waiting. We'll just go back to v blank 1. Just keep going back, keep going back. At some point, that's negative, and we fall through the conditional of the next one. So this literally is 2 loops that are while loops that wait 2 frames, which is what the comment says right there, right? And that is how you would do kind of a conditional loop or a while loop in assembly. Kind of gross, but also, like, if you know what the pieces are, like, okay, that it makes sense why that would work, perhaps. Josh?
And going through some of the code that you have on GitHub, PPU everywhere, what does that stand for?
Oh, thank you, yeah. So Josh wants to know what PPU stands for. It stands for Picture Processing Unit.
Okay.
That's the video card.
Okay.
Yeah, that's your video card. Ben?
How many instructions are there in assembly?
Great question. It's on another slide. For spoilers, it's 56. There are 56. For the 6502 specifically, remember every CPU has its own instruction set architecture. So like the original Intel Pentium has an ISA. The later things like Pentium 3, Pentium 4 generally add some instructions, but it's all backwards compatible to the first x86 processor, which means if you want to do stuff from the 16-bit days on your modern CPU, you still can, but you're crazy. Anyway, backwards compatibility is sometimes bad in hardware. The CPU, the instruction set architecture for the reference for the instruction set on the modern Intel chips is like 1,500 pages. Because it literally just keeps getting new instructions. They don't take out the old ones because you got to be able to run programs from 1992 or whatever. So these days things are a bit more complicated. The 6502 was a nice simple chip that had a nice simple ISA. And in general, there was a shift at the late 80s, early 90s where people said, we no longer care if like normal programmers can write our assembly code, because you should be using a language that has a compiler that will write the assembly code for you. There was a very marked shift at the end of the 80s towards assembly languages that were like much more complicated, but like also under the kind of design assumption that like no one's going to be writing this by hand, nor should they. Like a compiler can probably do a better job, so let the compiler do it. And there was a real shift in thinking at that time. Yeah. Other questions?
I think somebody has to write the compiler though.
Yes, and those people have to read the 1,500 or 2,000 page manual from Intel. That's part of their job. So, do you want that job? I don't know. Yeah. Are we having fun?
Yeah.
Are we learning things?
Yeah.
Cool. Okay, so anyway, it does a whole bunch of stuff after VBlank 1 and VBlank 2. Loads, comparisons, adding, subtracting. Not super, well, here's a decrement. That's a subtract 1. Not a whole bunch of crazy stuff. Down here at the end, it says, okay, fine, we're done booting, more or less. Jump to initializing memory. So here, this JSR is basically the closest thing you have to a function call. It says, go get memory set up for the game, and then we'll start doing whatever. Josh?
So as far as time, how much, like, milliseconds?
Well, so each instruction should take milliseconds, yeah, at most. And probably each single line is probably taking less than a millisecond. But we spend probably 16 milliseconds in this loop, right? Because we're waiting for a frame to come from the video card. But yeah, all of the instructions individually are very, very cheap. Yeah, though they do take different amounts of time. That's measured in something called cycles. So if a CPU has 1.79 megahertz, then it can do 1.79 million cycles a second. And each instruction takes a number of cycles less than 8. So you can and optimizing code in the assembly days meant either coming up with a better algorithm or cycle counting to try and figure out a shorter sequence of instructions that by some weird happenstance gave you the same result, kind of. So it got kind of bananas. I don't know about that stuff a whole lot, to be honest, but yeah.
Oh, it's pretty funny. That's my initials as well.
JSR.
JSR.
Where's the instruction to check if you blew on the cartridge?
I don't know where they put that. I've not seen that one yet. I looked. Warm boot is if you blew on the cartridge. Cold boot is if you forgot. Yeah. Okay. So good questions. All right. So a couple takeaways from this. It does not look fun to write. I don't think I would want to write this stuff, to be entirely honest. Like, I kind of am crazy enough to maybe be interested in writing a compiler from JavaScript to it or something, but like I definitely don't want to write just 6502 code. Like, nah, no thanks. But maybe running it's not so bad, right? Maybe writing a CPU interpreter, like a CPU emulator, would not be that bad. We just need a CPU object, right, that has the registers and methods on it for all the different instructions. Does that make sense? And then we just have a big array that can be memory, like a big array of numbers. That's basically what it is. So like that's not that bad. But there are some questions that you should have. Things like, well, how do we actually get the 6502 code loaded into memory and get the program counter set up in the first place? That's not entirely clear yet, right? One other thing you might wonder is like, okay, can we get a little more detail about like how data is represented? Like you said that the program counter is 16 bits, but all the other registers and like everything else in the system is 8 bits. So like, how does that work? And so I want to spend just a minute talking about that. This is possibly the least fun part of the presentation, depending on your perspective. I don't know, but we got to at least look at it for a minute, and then we can get into kind of some actually writing the CPU. So as far as numbers go, right, in assembly code, like we talk about bits and bytes. We don't talk about numbers. We rarely give a damn about decimal numbers. Like if you see a number in assembly code, normally it's not referring to counting on your fingers 1, 2, 3, 4, 5. Normally it's hex or binary, right? So the decimal number system, you all remember and know, like that uses the digits 0 through 9, and you can count it on your fingers. And as you move forward, as you move forward in the number, you're dealing with successive powers of 10, right? So the first digit is the 0th power of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. The second digit is the tens digit. It's the first power of 10. The next digit is the third power of 10. It's the hundreds digit, right? And so on. Binary works the same way. If you haven't seen binary before, or if you've seen it 100 times and this is annoying you, sorry. But binary works the same way. It's just that you only have the digits 0 and 1. So the best you can do is represent things in, so all the successive digits represent powers of 2 instead of powers of 10. The first digit in a binary number is 2 to the 0th, or 1. The second number in binary, or the second digit in binary, is 2 to the first, so 2, then 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16,384, 32,768, and more after that, right? So programmers get very familiar with powers of 2. Finally, hexadecimal uses the digits 0 through F, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A is 10, B is 11, C is 12, D is 13, E is 14, F is, thank you, yeah, it's 15. F is for 15. F is for 15.
Because you start at 0.
Okay, so brief demonstration. This graph I think is actually pretty nice. I found this on Wikipedia and just decided to steal it because I'm lazy.
Just like this one, we need have 16 fingers.
You can see them carrying, right? This only goes to 16, so this technically is working with a size of data that we call a nibble. That's a real word, I didn't make that up. 4-bit regions in programming tend to be called nibbles. Some people may ignore that. With a Y, yeah, nibbles.
I don't buy
Okay, good? How are we feeling? Is this okay so far? Is anyone in pain? Do we need medical assistance? Okay, so in JavaScript, it turns out there's support for all this stuff too. Regular decimal numbers, you already know how to write, probably. Hex, you just put a 0 and an X in the front. Then you can write hex numbers. So 255 in hex would be written 0xFF, which is 15 times 15. Josh.
No. So So 1F would be what?
15. That would be 15 plus 15. That would be 30, I think.
Okay. 0x.
Shall we check?
0xf.
31. So I'm sorry. 1 is 16. 1 because it's the first power of 16. Remember, powers are 16, right? So 1F is 16 and then 15. The F is 15. The 1 is 16.
So 0F would be 15, 16.
Yeah, 0F would be 15. 10 would be 16. 1F would be 31.
Okay.
Yeah.
Cool.
So that's hex. That's binary is just 0 and a B in the front instead of an X. And in assembly, the syntax varies based on what assembler you're using to read your code. There actually was a commercial market for assemblers in the 80s, and they tried to pack in lots of features so that it would be less of a pain in the ass to write assembly. Can you believe? So decimals 255. Hex generally, for our purposes, will be represented by a $sign at the beginning. Binary by a %sign. Cool? Everybody good? Okay, so there are 2 more slides of this. Sorry. Okay, so if we have an 8-bit CPU, then fine. We're mostly working with bytes. And because of limited storage, you've only got 8 bits. That means as high as you can count is 255, which is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That's 255. That's 8 bits. That's as high as you can count, right? You can count up to at most 255. So that's great, but then you got to wonder, what if I need a negative number? Or what if, as with the CPU's program counter, I need to talk about a number bigger than 8 bits? Like if the CPU for the Nintendo can address 64 kilobytes of memory, how do I talk about an address higher than 255? Because I'm gonna need to, right? That's important. So I've got some definitions here. I'm gonna go slightly fast through this, but ask if there's something that's bothering you. It's not only in assembly, but also in C, C++, I believe Java, and other kind of certain lower level programming languages. You'll hear about signed versus unsigned numbers. Signed numbers are where you're basically promising the computer it's always going to be positive, and so it's going to use all of the bits in the number to count as high as it can. Unsigned numbers, that's unsigned numbers, I'm sorry. Unsigned numbers are you're promising the computer it's positive and it's going to use all the bits and count as high as it can. Signed numbers use the very highest bit, the very last bit, the very highest bit, the top bit, as a positive or negative indicator. And that changes the range of numbers slightly and how it behaves. And so like a signed byte can't represent 0 to 255 because you're cutting the amount of data kind of in half. It can represent negative 128 to 127, which is kind of weird. We're going to talk about that briefly because you don't need to internalize all the details, but we will talk about that for just a minute. The important thing is that there's that signed bit at the top. And then a word, a word is sort of a processor-specific piece of terminology. It basically means kind of the address size for that processor. And in the case of the 6502, while all the registers are 8-bit, the address size is 16-bit. Right, it's got a 64K address space. So we'd say that a word in the 6502 is 16 bits. So the simple way that you represent 16-bit numbers is you just have 2 bytes next to each other. Does that seem simple? Like you have bytes, why not just have one address in memory be the first byte and one address in memory be the second byte, and then you got yourself a 16-bit number, right? It's just in 2 places, right? And you couldn't store it in a CPU register at the same time, but like you could do math on it, just as the high byte and the low byte. Okay, so that's basically how you store words in 6502 assembly. And the concept, there's this concept of Indianness. This is completely real. I kind of wish I was making it up, but I'm not. Which is just how do you order the bytes in memory? Which one goes first? If you've got a 2-byte number, how do you lay the bytes out? There are some philosophies about that. Most significant, there's one called, well, this slide was poorly designed. I was whipping these up this morning. There are 130 of them. It took a while, so I'm sorry we started late. Few more definitions. The most significant bit or the most significant byte refers to the one that's higher in power. Remember what I said on the last slide about the decimal number system and binary system. If you think of it as a bunch of digits, the whole thing, which one's the biggest? Which one has the most significance, right? For this binary number in the graph right here, this would be the top bit, the 0 right here, because it's 2 to the 4th. That's the highest power, right? That's the top bit. That's also sometimes called the most significant bit or byte. If you're talking about a word that's, you represent a word as 2 bytes, then it might be called the most significant one or the top one. The bottom would be called, maybe also you might see LSB somewhere. They're talking about the least significant bit or the least significant byte. Okay, so final thing, Little Endian and Big Endian. So in Little Endian, I'm not even kidding. This is so real. Okay, yeah, so something about oppression here. So Little Endian and Big Endian. In Little Endian and CPUs that have a Little Endian architecture, that's a real thing I said. In CPUs that have a Little Endian architecture, the little bits come first, and so you would write hex 2000 in memory as hex 00, hex 20. Those would be your bytes. You'd have a 00 byte and a 20 byte. Big Endian says the big bits come first, and 2000 would be stored in memory as the bytes 20 and 00. Questions about that?
Only jokes.
Only jokes. Yeah, I had a feeling. Will.
What's the Indian name?
What?
Do you know who came up with the name for that?
There is attribution varies, but I think an article in a journal in 1980 was the first one to do it. And there's actually a reference about how it started fights. Like if you look up Indianness on Wikipedia, etymology. Danny Cohen introduced the terms for byte ordering in an article from 1980. In this technical and political examination of byte ordering issues, the Indian names were drawn from Jonathan Swift's satire, Gulliver's Travels, in which civil war erupts over whether the big or the small end of a soft-boiled egg is the proper end to crack open. Showing that this is a stupid discussion and people fight about it a lot because computer nerds fight about everything. We know that, right? Okay, so which one of these delightful Indiannesses do you think the MOS 6502 and also your modern Intel chip use?
Little.
I don't think big.
Big seems like it would make sense, right? Because that's how we order numbers normally.
But this is bananas, so it's little.
But this is bananas, and it is in fact little. This is not a trick question. There are things called mixed Indianness where you actually have both. We're not going to get into that. But all modern Intel chips and the MOS 6502 are little endians. So if you see an instruction like store, there's no constants in here that are big. If you saw an instruction like store 2000 right here, your brain says, oh, that's an STA instruction in memory, then a 20 in memory, then a 00 in memory. But it's not. Flip those, because it's little endian. You having fun yet?
Yes.
Ben.
Is that?
This is
I'm trying to
so
think,
real.
Is that not one of the main difference between Mac and PC?
No, but I mean that there are a lot of differences between, like, if you think about the 90s wars between Windows and Mac and how they had like no file formats could be used on both and like all this kind of stuff. Issues like these are partially responsible, but are far from the only thing that makes programs incompatible across CPUs. So the Mac, for those who are curious, in the 90s at no point used Intel processors. I believe they were using PowerPC up until 2000. I mean, they were using PowerPC in the 2000s. In the 90s, I don't know if they were using, I think they were using Motorola 68K chips for a while, and those have completely different instruction sets. So if you think about that, what that means is porting programs between processor architectures can be complicated if you're writing in a low-level language in the first place, because you might be making assumptions about how the processor works. So that's a good question, though.
It just seems like when things got beyond 16-bit address sizes, that the little Indian would have gotten more confusing. Because is it?
Yeah,
because
you'd think so. So I don't actually.
You would still start at the very end, and even.
So the big difference there is that because all the registers in a modern CPU are either 32 bits or 64 bits. So the word size in a modern Intel machine is 64 bits. Mm-hmm. But I believe the register sizes are 64 bits too. But even if you wanted to refer to something that's 128 bits, which you're not going to need to a whole lot, but like if you think back to the 90s and the early 2000s when we had 32-bit computers, they generally could deal with 64-bit addresses without a lot of difficulty, because instead of saying the low byte and the high byte, you'd say the low word and the high word. And so then the whole word might be stored in a register in the correct order. You'd still only have two pieces. You wouldn't have like 8 bytes that are all backwards. It didn't scale up like that. Does that make sense? Yeah. So like even on a modern CPU, like it's not wildly worse than this. Other things are wildly worse than this, but not that. That's about the same. Will.
So what does a bit look like?
A 0 or a 1? Is this a trick question?
No, I'm just, so an 8-bit CPU.
If you go back to your chart, your binary chart,
yeah,
that represents.
That represents half a byte. If you want to imagine a whole byte, just add a 32 here, a 64 there, and a 128 right there.
Yeah, 8 bits make up 1 byte.
Right, and that's for an 8-bit CPU.
Mm-hmm.
So if it's a 32-bit,
it's literally just 32 instead of 8. Like it's just longer.
It's still 8 bits.
And 32 bits.
Yeah.
Okay, so it is 8 bits as a byte.
8 bits is a byte always. Yeah.
So you'll see on commercials like, oh, we give you megabits per second. It's lowercase b. It's actually like 8 times.
That's a whole other thing, but yes. Okay. So final slide of this, and then we get to the fun stuff, right? So how do negative numbers work? Oh boy. Well, there's this thing called 2's complement, which is kind of goofy. I'm not going to go too in-depth about it, but the high-level points are these. It's used for signed numbers on modern computers, but it doesn't represent numbers. Like you might think, okay, like I lose the last bit to knowing if the number is positive, or the top bit. I lose the top bit to knowing if the number is positive or negative. Then the rest of it should be 2 to the 7th. Like, so if you're talking about a byte, it's got 8 bits, right? So you can talk about numbers up to 2 to the 8th. If the 8th bit is being used to know if it's positive or negative, your intuition might tell you, like, then I can talk about negative 127 to positive 127. Or negative 128 to positive 128, because that's 2 to the 7th, right? I lose 1 bit. Instead of 2 to the 8th, it's 2 to the 7th. It's not actually the case, because you have to represent 0. You have to have somewhere to put 0. So the way that it actually works is the negative bit is you can go slightly higher negative than positive, which makes sense because otherwise you could just use an unsigned number and then you got plenty of room. So you can go from -2 to the n minus 1 for whatever your like bit size is to +2 to the n minus 1 minus 1. In practice for us, that means you can count from 128 to 127. The top bit, if it's 0, that means it's positive, and if it's 1, that means it's negative. Now, one thing, a quick note I'd like to make about that: you could pass a byte around and use it as an unsigned byte in some places, and a signed byte in other places. You don't have to care at at a certain level. At a certain level, it literally is just bits, and it's fine. And that's actually why they use 2's complement. So, okay, we'll talk about a little bit more about that in a second. So, kind of surprisingly, if you look at it, 1, 2, 3, 4, 5, 6, 7, 8, that should be 255, right? That's as high as you can count, is all ones. Whereas, this is not as high. You might think then that if you're doing this, actually, I can't say unsigned to JavaScript, so this will not work for this demonstration. I don't have a way to tell JavaScript I want this to be unsigned, but I do have some scratch notes about this. You might assume that in unsigned numbers, 0b11111 is oh crap, sorry. You might assume that 0b11111 would be 128, but that's not how it works, which surprised me when I was first learning 2's complement. I was like, who the fuck designed this? This is crazy. And 0b1000 is negative 128, and that was confusing to me. But the reason this works is because what you're basically doing is starting, as soon as you see the 1 in the top bit, just say the number that we're starting with is 128, then just start adding back up towards 0 for all the other bits. That's basically what you're doing in 2's complement. And that was the intuition that until I had that intuition, I was like, this is the weirdest thing in the world. You're not subtracting from 0 when the top bit is 1. You're adding to negative 128. This should say negative right here. It doesn't. But that's what you're doing in 2's complement. Now, the reason that we actually bother with this are for 2 points. One, there's no negative version of 0. There is an alternative system of doing this in mathematics called 1's complement. And it's not fun, because all of a sudden, anytime you're dealing with 0, you have to figure out if it's a negative 0 or positive 0. Oh, it's bad. You don't want that. There should only be 1 0. Didn't your math teacher tell you it's not negative or positive? This 2's complement kind of cheats by lumping 0 in with the positive numbers, but fine, it's a representational issue, right? That's fine. So that's one reason that we bother with this, that we put up with this. The other is that addition, multiplication, and subtraction actually wind up working the same on signed and unsigned numbers, which means most of the time you can ignore what it is. You can ignore whether it's signed or not. Because addition and multiplication and subtraction work the same unless it gets bigger than a byte. So here's an example of that, because I was convinced that there was no way in hell that explanation would make sense. So here's a 2's complement representation of negative 102, right? So this is negative 128. Then we add, 32, 16, and no, that's 64. That's 128. That's 64. That's 32. That's 16. And then, no, that can't be right. Wait a minute. Imagine a 2's complement representation of 16, 8, 4, 2, and 1. Thank you. So that's 16 and 8. That's 4. So the total here is we're starting with negative 128 and adding 26. Yes. And if you add 26 to negative 128, you get negative 102. Then we have an unsigned number here. This could perfectly well be treated, this number with 0 in the front. We could totally treat that as either signed or unsigned. It doesn't matter. It doesn't matter. Because it doesn't have a 1 for the top bit, we really don't care. We're happy to just add these two things. Addition works the same either way. And that's even true for this one. This could be a signed number. And if it's a signed number, then it would be, so if we're treating this as, this could be an unsigned number. If it's an unsigned number, then that would be 128 plus 16 plus 8 plus 2, which would be 10, 26, 128 plus 26, 140, 154. And it's perfectly fine if you want to do the addition or the subtraction either way. So if you say if you say what's 0B111, or if you say, fuck, here we go. So if I tried to add these two things together, I would say, well, let me start at the end. That's the only way I can ever do this. So it's 0, then these two ones add, those turn into a carry, right? Because that overflows. Like if you think about decimal, if you add 5 with 5, you'd have to carry a 1. Same thing here. I add a 1 and a 1. I carry the 1. This 0 becomes a 1. Here's 2 more. That becomes a 0, but I carry a 1 here. 1, 1, 1. That winds up being a 1, but I also carry a 1. This winds up being a 1, but then we have a carry, so that's a 0. This winds up being a 1, and then there'd be a 1 in the front because here's this 1 in the front. Okay, that's what happens if I add these two things together, and that is 128 plus 64 plus 16 plus 4, which is 128 plus 84, which is 212. And down here, I'm saying if it's assigned, so here's the sum if it's unsigned. Here's the sum if it is signed. You'll note that both numbers are completely identical. You'll note that both of these numbers are 100%, like if you look at the bits in the two sums, it's the same. It doesn't matter if I treat it as signed or unsigned. Either way, I can interpret the answer, and the bits are the same. That's a magical mathematical property. That should seem like weird voodoo tricks, and it kind of is, but someone I don't know wrote a proof about it, and so we can accept it as fact. Because that's how math works. Computers don't always necessarily work that way because your framework breaks, but that is how math works, right? So because of this, we don't have to care if numbers are signed or unsigned. If we want to treat a series of bits as signed, we can. If we want to treat it as unsigned, we can. And that's a really nice property to have in terms of where you store things, how you use things based on where they're stored. You don't have to always be keeping track. You can just use it when you need to. That's a really nice property. That's a very special property. And that's really the reason that we put up with 2's complement, is because addition, multiplication, and subtraction work the same on unsigned and signed numbers. I don't know about division, but I assume that it's fine because hardware designers have been using this for 30 years. Okay. Let me take questions about that for a minute.
How does the CPU know if it's signed or unsigned?
Based on the instruction, basically. Some instructions will say, like, I'm going to treat this as negative. Some instructions will say, or like, treat it as signed. Some instructions are like, I don't care. So it comes down to that. Yeah. Well, and actually, it doesn't even come down to that. It comes down to where you read it and how you read it. So the bits are the same whether it's signed or unsigned, right? That means it's up to the programmer, when they're using a number, to decide if they want to use it in a negative way they can. And then you just have to keep in mind, like, the thing I'm storing at this place in memory is signed. And when you're using it, like, use it like you would if it was negative. Otherwise, you'll read the number wrong. Not the most fun, but, like, it works. Cool? Kinda, right? Kinda. Okay, other questions? Rickard. You get overflow, and I'm not prepared to cover this here, and I don't know what 2's complement says about that. I implemented the processor, so whatever the processor does, my emulator does, but like, I don't know. Great question. It becomes, yeah, it's simple until you have overflow. When you have overflow, then there are some special rules, but like the processor implements the rules, and it's basically it carries. You have to do carrying across bytes. Yeah. Okay. All right. So enough of these numbers. Enough for these numbers. This is bananas. Enough for the numbers. Like, let's think about like how we could load a game. All right. So, have you ever heard of ROMs? Julia Stiles flashback time. Y'all, I'm sorry I had to include this GIF. This is real. The 90s were a really special time.
How about letting me write about the hacker for the next issue? Do you know anything about hackers? Can you jam the console cowboys in cyberspace? What? Ever read Neuromancer? Huh? Ever experienced the new wave? Next wave? Dream wave? Or Cyberpunk? I didn't think so. I'll handle the hacker stories. Yeah, I guess you should. We should learn about all this hacker stuff. In there. It's a world where you're judged by what you say and think, not by what you look like. A world where curiosity and imagination equals power. We need more paper. Let's go, people. Work with me here. Work with me.
The 90s were a very special time. That could ever be on TV is hilarious and amazing. Okay, so ROMs. Game cartridge data, people made tools to read it off the cartridge back in the 80s or 90s, I don't know when. Special hardware, and then they read it into computers and just saved it, because computers had a bunch more storage than Nintendo did. So you can download these files. It's not legal, but who cares? Nintendo doesn't seem to be litigating, so I wouldn't worry about it much. This stuff there's not a retail market anymore. Nobody's buying Nintendo games. Like, it's fine. So the Nintendo ROM files that you can find on the internet and download, I won't tell you how, because then I'll get prosecuted against maybe, I don't know, are in a format called iNES, because they were originally came up with by the guy working on the iNES emulator, one of the first Nintendo emulators. And the simplest to understand documentation I've found about that format is here. And it basically says the TLDR of this documentation, which is like so simple and clear to me, like that is technical documentation I'm happy with, that's fine. Basically, if you've never worked with a binary file format, the deal is this. You open a file, but instead of text, you ask for numbers. You ask for just a binary array of bytes back. The first 16 bytes in the file, and if you're doing binary file loading, like it's probably going to be in bytes, not in machine words or whatever. Like on this CPU, if you think about it, I could read the file in 64-bit chunks, but generally, if you're bothering with doing like binary file reading, you actually want to get at individual bytes anyway, so you'll get it back in byte format. So the first 16 bytes are metadata about the cartridge, like about the game. Everything after that is the actual binary data, just the array of numbers that is the game. That's literally what the ROM file format is. And that seems pretty great, because that means like, okay, we can just load everything after 16 bytes into memory. Here's the game. And we're golden. There's the game. It's loaded into memory. And we just need to be able to read files in binary for now. So here's how I did that in JavaScript. It's not actually that bad. The high-level view is there's a thing that's a new browser API. There are so many browser APIs these days, y'all. It's really a wonderful time for doing browser hacking. Like, there is all this stuff that you have access to that is like a lot of stuff. Like, it's kind of bananas. Web elements, audio elements, video elements. You've got like oscillators and filters in the web audio APIs. More on that another time. But long story short, you want something called a file reader. You add it to your page, and then you can give it a callback to process data. And I wanted to have it build some kind of JavaScript object, which I decided to call a cartridge. Guess why? And that's it. So here's the code to do that. This is actually one of the very first commits on the project back in August. Basically, I had a file input somewhere, right here, input class file input, type file, right? And then inside the app controller, I got the file input, which I don't remember what it was. I create a new file reader as this.reader, and then I have some ROM load handler, and what that does is it sets up a callback for the reader for when you actually have selected a file. And then it says, find the input on the page, and when the user, or find this class has changed in the code since I wrote it originally. But, wait, no, it hasn't. Input. There was a bug in this code when I first committed it. That's what it is. Anyway, find that thing on the page, and when that has an event called change, which is what happens when the user selects a file. Capture the event, and then let the file be whatever. You actually get back this event target that has an array of files. Just grab the first one, because it's a single file input, not a multi-file input. So grab the first one, and then do this.reader, read as array buffer. Now the reason that, and pass it the file. The reason that I have to give it a callback, this onload callback, is because read as array buffer could take not much time if it's a small file, or a lot of time if I gave it a 5 GB video, right? So I have to give it a callback. The callback is this.swap cartridge. I want that to have access to other stuff in this object, so I have to bind this, which is a JavaScript scope thing that is really the only thing I've been mad about in JavaScript in the entire course of this project, other than undefined. I've found it to be a perfectly nice implementation language. More on that another time if you want to talk about bind or you want to go through why I had to do that. I'd like to, but not at this moment. So I just bind this and then call swap cartridge. Swap cartridge says, okay, I'm going to create a new, literally a byte array. You can say I want to create an array just of bytes in JavaScript these days. That's how you do it. And for performance reasons, that might be good. If I do that, it's going to let the compiler know like all the stuff that goes in here should be bytes. And it might be able to do things that are faster because it doesn't have to check how big the numbers get in assembly on my machine, on the Intel. Okay, so anyway, I say this.reader, after it's finished reading the array buffer as bytes, should have a result. And I want to turn that into a array of bytes. Like I want to take that thing, which I think is some iterable object. I don't exactly remember. But long story short, you can say turn that into a byte array for me like this. And then I had a method on the CPU's memory called swapcart that takes the data and basically swaps a cartridge into the Nintendo. Imagine that. I think that's down here. This is the actual cartridge class. It takes in some data, pulls off the header, which is those first 16 bytes, records that information based on that guy's technical document, which we don't need to go through in too much detail because it's not super important to this, but like the key thing is certain bytes in that first 16 mean different things. I save that, store that out, and then say the rest of the data is whatever's after the first 16 bytes, and that's my cartridge. And I've got a game cartridge. And then in memory, I just say this.cart equals new cartridge. All right? Not bad. Not super bad, I hope. Questions about that? Kenny.
If you scroll up right there, the last object in the array, an object, the beer game,
Yeah.
it's a single interesting.
Oh yeah, we gotta. Okay, so this is some like bitwise operators. So the single ampersand is something called logarithmic and, or bitwise and I would love to talk about that in a minute. But I would love to talk about those things. That you might notice this looks kind of funny too. Angle, or greater than 4. There's some funny stuff like that we should chat about in JavaScript. Let's hold that for a little bit to Q&A. Is that cool? Yeah, good question. It's math, basically. But it's math on bits, not on numbers. Okay, and if you want to know, I think, there's this page, which you might notice came up in my browser history really quickly, called Bitwise Operators on MDN. I may have consulted this page a lot while working on this project. Because documentation, we all need it. Professors or instructors are not special. The one other detail to know about this is when the Nintendo is turned on, or when you swap cartridges and hit reset, what the hardware physically did is it just set the CPU's program counter to the last, the second to last word in memory. So literally whatever is in memory at 0xFFFC at that time when you reset or turn on the Nintendo, that's the program counter, and it jumps immediately, or the program counter is read from that. So whatever is stored at 0xFFFC and 0xFFFD just gets read right into the program counter, and the CPU starts working.
Like
and so whatever
knows how to boot.
So it knows how to boot. So it knows where in the code to go to start running the program. It's literally why you put stuff there. And so, for example, for our Super Mario game, sorry, there are a lot of constants. Like a lot. Imagine you only have global variables. Start here, whatever the address of start is, would be stored in those 2 bytes. Right? The address of start would be stored in those 2 bytes. And then Nintendo would just go there, start working. Okay. Cool. Feeling kind of good, kind of cool. Got some things, kind of complicated. Okay. So, 6502 in JavaScript. How do you do it? Well, on a simple level, we need a couple different things. We need a class, again, to represent the CPU and the registers, the different data the CPU stores directly. We need methods on the class for whatever instructions the CPU has. We need a big array of numbers to be our memory. Then we can make an instance of memory, or just use an array, make an instance of the CPU, load the cartridge, and then bam, just like start running, right? Cool. So how many methods do we have to write? So Ben was asking this earlier. The answer is the 6502 has 56 instructions. Don't memorize them. We're just going to skim through them to get a general idea. I've grouped them into 5 categories because I think that makes sense. So you've got math and logic instructions. So rotate left and right, which rotate might not make sense immediately when you read it. You're like, what? But if you have a number, write the number out in bits. Rotate left moves all of them to the left, bringing the one on the far end around to the beginning. Rotate right does the opposite. Takes the one that's on the beginning, moves it to the end. I don't know how I feel about this beginning and terminology. I think I'm mixing stuff up. But like it just rotates all the bits to the right, and if one gets pushed off, it goes around to the other side. That's rotating a number. It's rotating the bits inside the number. You've also got shift left and right. Those those do the same thing as rotate, but if a number gets pushed off one of the ends, it just becomes 0. So like if you had a number that was 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, and you shifted it left, it would be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then there would be a 0 where the 1 used to be. Not because there was a 0 on the, okay, you could have a number that's all 1s. If you shift it left, it will be all 1s and then a 0. Because the number on the left that like gets dropped, basically. So shift and rotate are very similar. Add and subtract should not be surprising, right? You've got addition and subtraction. It's very common to want to add 1 or subtract 1 from things. So, or to add to a number or decrement from a number by 1. So you've got increment and decrement to modify arbitrary regions of memory. Incs, NY, DEX, and DEY are for specifically the X and Y registers. They're specifically for the X and Y registers. You've got compare and compare X and compare Y, which basically it's close to equality testing. It's not the exact same thing, but it looks at 2 numbers and leaves some stuff in the status register that you can check to see what the result was. So you might do that before like a branch operation. Like compare these 2 numbers. Are they equal? Okay, branch. Like if, a branch is an if. So you've then got and, or, and exclusive or, but these are logical. These are logical and an or, not. You've got a logical and an or and exclusive or. Those are bitwise operators as well. Those are not. I've written this here and I shouldn't have. It's not the same thing. These are single ampersand and single pipe, not double ampersand and double pipe. And then finally you've got bit, and I honestly forget what it does. You've got moving data. So obviously you want to move data around. That's something pretty common. So you've got load instructions for the accumulator, the X register, and the Y register that pull data from memory. Store instructions to take the stuff in those registers and send it to memory. And finally, you've got a bunch of transfer instructions that literally just swap the things into registers. That's not even right. Tax, for example, takes whatever is in the accumulator and puts it in the X register instead. Tay takes the accumulator, puts it in Y. And the S is for the stack pointer. So like this takes whatever's in the X register, just puts it in the stack pointer. So you've got some transfer instructions.
Like a lot of those instructions
in Mario,
they duplicate each other a lot, except for where they're actually taking information from.
Yeah, absolutely. There's a lot of duplication.
Instructions, a lot of them duplicate a lot.
A lot of the instructions do. So you might notice that there are a lot of variants of instructions. Yeah, for like slightly different things based on if you want to use a different register. Commonly, that's because you want to use a different register, or you want to use an arbitrary place in memory. Like Inc and DEC are the best place to see that, I think. DEX and DEY are specifically for X and Y because you might have something loaded in those registers a lot. In fact, it kind of is encouraging you, if you think about it as the programmer, like if you want to add or subtract stuff, maybe throw it in the X or Y register. If you want to do it just somewhere in memory, not in a register, then you would use Inc or DEC. Ben.
So that's what you used your awesome macro for.
That's what I used. That's almost what I used my awesome macro for in the Lisp version. Yeah, almost. We're almost to that. That really was for something called addressing modes, which we'll get to in a second, which is the final wrinkle in assembly programming for my, it was the final one on the CPU level for me. And we're just doing the CPU today, so we're actually most of the way through the lecture, so don't panic if you're like, oh God, like this is also why we're not covering graphics and audio today. Aside from the fact that I don't have the code written, you might imagine we'd be here a while. Well, I have the code partially written. Never mind. Yeah, that's fair. Wishful thinking. Okay, so there's one more page of these because 3 more categories. So there's branching and control flow. So all of these are if true, if false. So branch if the last result did not have a carry. Branch if the result did have a carry, so the carry bit is set, is the mnemonic here if you're looking for a mnemonic. Branch if the carry bit in the status register is set, so there was a carry last time. Branch if 2 things are equal, branch if they're not equal, branch if the last thing was negative, branch if it was positive. The MI stands for minus. Branch if it was negative, because you already used BNE for branch not equal, so you can't say, you gotta do MI for, okay. So branch for negative, branch for positive, branch if it was bigger than a byte, branch if it wasn't bigger than a byte, branch if it was bigger than a byte. Jump, which is literally just change the program counter to this. JSR, which is the closest thing you have to a function call. So the way JSR, and this, I'm going to briefly talk about this because it's nice to kind of have an intuition for how like interrupts and things worked and how programmers didn't go crazy when they were doing this. So JSR is jump to subroutine. It's the same as a jump, change the program counter, right? But before you change the program counter, you take the place where you currently are, go to the next instruction, and push that on the stack, along with the status register in the processor, whatever the processor's current status is. So you take the current status of the processor, take the current program counter, put those things on the stack, then you jump to wherever the thing says. You can later use RTS, return from subroutine. It'll take you back to whatever the last status and program counter was on the stack. So that gives you a way to unwind and kind of have something close to a function, but you have to manually kind of do that piece. So that's, right, it's a little hairy, but that's the idea there. The idea is that if you keep the program counter and the status of the processor on the stack, you should be able to go back. Okay, finally there's break and a NOP. A NOP literally is called no operation or do nothing. Break is kind of like halt, enter the debugger. It varies based on the system. And then RTI is similar to RTS. It looks on the stack for a return address. Similar thing there. Finally, there are literally some operations just to mess with the status register to clear set the carry flag, the decimal flag, the interrupts, overflow, etc., stuff like that. Cool? So that's all told. Fifth category. Sorry, stack operations. You might want to, if you're putting stuff on the stack, you probably want to get things off it. So you can push and pull stuff from the stack into the accumulator or into the status register. Yeah. Okay, so 54 instructions, or 56 instructions. Not that bad. I mean, we'd have to write 56 methods, but like, okay, all in a day's work, like 56 methods, fine. That's not, that's not super hard. Unfortunately, the 6502 has 150 or so opcodes. So it's not just that these things have, and it's not just that CPUs, in assembly language you have instructions. You have multiple variants of instructions that use things called a given addressing mode. And this is something that I've wondered how to explain to people for the longest time, and I think I've got something that might be okay. Tell me how it catches. We're going to talk about this after this slide, and then I'll show you the code, and that's basically it. Bob's your uncle. So if you recall from earlier, we said, when you're programming assembly, you don't have variables. You have registers, and you have addresses. That means if we want to use an argument, we have to know its address, right? If we want to pass some data, we have to know where it is. But remember, Nintendo registers are 8 bits, but the address range is 16 bits. So, because there's 64K of addressable memory. So there's a little bit of a problem there, right? Like, it would be really a pain in the ass if any time I wanted to refer to an address, I had to use the full 16 bits. Like, that would be bad from a storage perspective, because anytime I wanted to use an address, I'd have to use 2 bytes of, like, pretty limited memory, right, instead of 1 byte. And above and beyond that, it would also be more expensive on a performance level for various reasons. So, because if you know there are certain places where variables will be stored commonly, you can make access pathways in the hardware to get there faster, which is what they did in the Nintendo and in the 6502. So address modes, also there are many common patterns of accessing memory, right? Sometimes you're like looping over an array and you have a start index and then like an offset, like for I equals 0, items I, and then you bump the count of I each time, right? That kind of thing. That's called indexed access. You do indexed access all the time, like to loop over an array or something. And so there might be ways that we could design addressing modes to make that easier to do on the assembly level. So that's why addressing modes exist. They basically are functions. You can think of an addressing mode roughly as a function that tells you where to get your data if you're an instruction. Like you run an addressing mode, you say, you call, if you imagine it, it's a function that computes an address. That's really all it is. So each instruction on the Nintendo, each of those instructions we were looking at, supports one or more ways to have arguments passed to it. One or more ways to have arguments passed to it. Some support as many as 8 different ways to be called, to have arguments passed. And those different ways are the things that we call addressing modes. And each pair of an instruction, which is one of those named, commands, and then an addressing mode is what we would call an opcode. So it's a specific version of the instruction that has a specific byte representation in memory. That's an opcode. Okay. Questions about that, and then we'll look at the addressing modes. Ben?
It sounds like it's context for the instruction.
It's context for the instruction about where to get its arguments. Yes.
And does the addressing mode come from the cartridge?
The addressing mode is built into the CPU. It doesn't come from the cartridge. It's a very good question. And it knows which addressing mode based on what the number in memory for the instruction is. So let's look at, I prepared for this. Let's look at the Super Mario Brothers boot code one more time, but this time we'll look at it in Nescavation. Hey y'all, look, it's some code I wrote. Okay, so this is the Super Mario Brothers boot code in Nescavation. Ooh, wow. Okay, so here we've got SEI, then clear decimal, then some loads and stores, right? All that kind of stuff. Okay, but here's where it gets good. So look at all these loads right here. Here's a load from a static address that's 0, I don't know, is that 0 page? It's something. What byte is used to represent the load instruction? A9, right? Down here, there's another load using a 2-byte address. What byte is used to represent LDA? AD, not A9. So if we're talking about the actual hex, then those are those opcodes. I would say those opcodes are 169 and 173. Okay, but the actual byte that's being stored in memory tells you which addressing mode you should be using with the instruction. That's what tells you, is that there are different, literally different bytes used for the same instruction.
So the byte that comes from the cartridge
says which addressing
tells you
mode.
which context.
Yes. And the way that worked out in assembly is the arguments are written differently based on the addressing mode. So like if you look right here, you can see that off the top of my head, I think this is a 0 page mode. Or it's an immediate. No, it's an immediate. It's an immediate. So if the byte is literally the next thing in memory, then we call that immediate mode. And you write that with a pound followed by a $sign. If the byte is in memory, but it's like somewhere else, that's called 0. That is kind of 0 page. That also might be relative. And you print it like this. So you just print it. Technically, you normally would be using a label here, but my disassembler doesn't currently support labels because I don't know what labels the programmers wrote in the first place, right? I don't know what they called things. So anyway, but that's a relative mode instruction, and this is an absolute mode instruction, and you can tell that because it's $sign with a 2-byte number after it. But it literally comes down to that. And so they both, the instructions have a different byte representation in memory based on which addressing mode you're using. The arguments can be both read straight from memory, i.e. disassembled, like what I'm doing here, and assembled, and the syntax used for the argument lets you know for sure what addressing mode is being used. The bulk of assembler syntax is literally just learning the addressing modes. How are we doing out there? Everybody alive? Mostly alive. Kenny.
How come it jumps from address 8,004 to 8,007?
Because this is 3 bytes. So this instruction begins at 8007. This instruction begins at 8004, but because it has the instruction's 1 byte, every instruction's 1 byte on the 6502, but it has a 2-byte argument, an absolute address.
So the AB is 8004, 00 is 8005.
And 20 is 8006.
Yeah. And then the next instruction starts at 8007.
Yes.
So that's what we were talking about. It bumps.
It bumps. It bumps by however many is needed for the bytes of the data, which is based on the addressing mode, basically.
So if there's only one variable, it's just going to, so that 8000A is 8007.
Yeah. This is hex. So because this is hex, 8000A is actually 32,778. And I believe we started at hex 8000, which is 32,768. And there's actually a good reason for that, but I won't get into it right this second. Okay. See, y'all can read assembly code. It's not that bad. There are just some details.
So, like, I guess my thought is how do you write a game? Do you have to write it with flags that say your addressing mode, whatever?
You would be thinking, when you think about where to store data, when you're writing a function, so the question was, how would you actually use this when you're writing a game? I haven't done that, so I don't know. But my assumption is, if you're writing assembly code, you're thinking about where you want to store things in memory in very serious ways. And you probably start by graphing out, rather than like, what's the page layout, how do things react? You probably start by graphing out, like, what are my pieces of data? How am I going to represent them in bytes, and where in memory do I need them to be? And where in memory do I need to be probably is partly about like how often am I accessing them and from where. That probably helps you figure out where in memory they need to be. Once you answer those questions, then you can start writing code and you'll know the addressing mode to use based on where the stuff is going to live, where the bytes are going to live. And then you just have to look up the syntax for the addressing mode and go. Cool. And that's basically what a compiler for, like, if you use a language that's compiled these days, which could be something low level like C, it could be something high level like OCaml. The computer is doing something like that internally to figure out what to do with, your data. And the x86 processor still has instruction modes or addressing modes, and they've got to make distinctions about that kind of stuff. But the compiler figures it out for us so that we, and tries to write the fastest code it can so that we don't have to, because this is hard. It's a pain in the ass more than it's hard. It's really mechanical, but it's not fun mechanical, right? It's not like solving the problem. It's solving the problem around the problem, also called yak shaving, a very common programming activity, right? Like you get wrapped up in not really the thing you're trying to do, but the thing that you have to do to be able to do the thing that you're trying to do. Very common programming problem, right?
Like what's the...
So the joke about yak shaving is something about like I don't remember where yak shaving came from. It's an old programmer thing, but it's the last step of a series of steps that occurs when you need to. It's like it just keeps going. Basically, yak shaving means like I have to do this before I can get to the problem, but then whatever you're yak shaving is kind of endless and it just keeps going. There are a lot of jokes about that.
I was just trying to figure out like.
I don't know. Okay. All right.
Why am
I shaving the yak?
Why am I taking the time to shave my yak?
Fair point. So you probably would rather.
To make something else easier.
So you'd probably just play Mega Man, I guess is the answer, right? Like so that I guess the biggest thing that you can take away from this talk is like don't write games, play them. Like there's really not a good reason to write games or emulators for games unless you're crazy, but like just play them. It's more fun. It's more fun. Yeah, it's probably more fun. Okay, so we can see that there are like different, I was wrong here. There aren't 2 different LDA instructions. There are 3. There's one for immediate addressing, one for 0-page addressing, and one for absolute X addressing. So let's talk about those just briefly. So what are all the addressing modes? There actually are not a ton. Oh God. Okay, I apologize for this slide. There's implied mode, and that basically means the instruction doesn't take an argument. An example of that would be clear decimal. Oh, wait, I've got it over here. Sorry. So an example of an implied mode instruction would be either of these first 2. They just don't take an argument. There's no argument. The processor already knows what to do. right? It doesn't need an argument. Then there's immediate mode. That's when a constant is literally stored in the next byte. It's the next byte over. An example of that is this LDA instruction right here, pound $, constant, in the next byte, right there. Yeah? Cool? Okay. Accumulator mode. It's very similar to implied. I think that this was in there only so that in the assembly, like I don't think this mode technically is like in the documentation of the processor or necessary, but there are certain instructions that can be used for multiple things or like have multiple addressing modes, and one of them is to work on the accumulator directly. And in a lot of assembly languages, you'll see them write like the LSR instruction, for example, and there will be an A after it. And that just means the version we're using is the accumulator version. To me, I would kind of lump that in with implied and not have a different syntax or something. I don't know, but you'll see this referred to many, many places as accumulator mode. It's kind of common. Zero page. So zero page is the memory range from literally from the bottom of memory. The first page. A page is generally 256 bytes. So from byte 0 in memory to byte 255. That's the zero page, the bottom page of memory. And it's very common for frequently accessed variables, and it's cheap. Like, it only takes 1 byte to talk about anything in there. And so a lot of programmers argue, like, some people are like, the 6502 sucks. It only has 3 registers. And some people are like, no, man, it has 259. Because, like, the zero page, right? Because, you know, all of a sudden it's very easy to work with any data that's in that bottom page. So zero page is super, super common in 6502 code because, among other things, the CPU can get stuff out of the bottom page of memory slightly faster. So you save a cycle of CPU usage. Because you don't have to go, and it's actually because you don't have to go get the second byte for, like, an absolute address. An absolute address can talk about the full 64K, but the CPU burns another cycle going to get, you know, whatever that second byte of the program counter is. That takes a second. So, okay. There's also zero page X and zero page Y. They literally do indexing and offsets like you might think. It just adds whatever's in the X or Y register to whatever comes back from the zero page. So it gets whatever is in the zero page address, or it looks at the argument you gave, adds the X register, the address you gave, adds the X register to it, pulls the argument from there. Same thing for Y. Absolute is the same idea, but for 16-bit addresses, so the full address space from 0 all the way up to 535. Then there's indirect. This is used for pointer chasing. If you've ever done C programming, I haven't, but I sound cool right now. This memory address, basically that means the memory address that we give you holds another memory address. That one holds the data we actually want. So that's called an indirect access. We haven't seen one of those in the code, in disassembly listings yet, but generally, let's see if I can dig something up. So let's just step the processor for a second. Oh, just jump me a frame or two. There we go. Okay, so here's how you typically will see the X and Y modes denoted in assembly code. It's just, so this is absolute X. Here's the address. Add the X register to it. Right? Does that make sense? So that's how you typically will see the X and Y versions. They just have a comma and then the register off the end in the assembly. Indirect. God bless you. Okay, indirect. So indirect is generally represented with parentheses around the address. So rather than this syntax where you have like $, you just wrap parentheses around it. That means it's an indirect access. Finally, there's relative. Relative is exclusively used for branching. So if you need to like in the BPL instruction where we said go back to v_1 and keep doing that until a frame is passed. That's done with what's called relative addressing, and what's actually stored, like the byte. So if we look at BPL right here, what's actually being stored right here, this FB, is a signed offset of how many steps to go back to get to wherever you need to be. So starting from this instruction, which is at 8012, go back FB steps to get to the instruction you want to run. I don't know what FB is in whatever, but basically it should be jump back, 2 bytes, 3 bytes to get back to 8000F. The reason it's an offset, I don't know. I guess it's because when you're branching, you only kind of want to go back or forward. And if it's an if statement, you probably aren't trying to jump into like a function a mile away. You're probably trying to go pretty close. So in assembly, you can basically branch to anything pretty close, like 128 bytes plus or minus, more or less. There's something else about that that's important that I'm forgetting. Normally, programmers would not memorize the offsets and write or like do the math and figure it out themselves, because you can imagine that would be a huge pain in the ass. One of the first things a decent assembler does is lets you have labels, like we saw in the thing earlier, where you can just write in v blank 1, and later when you assemble the code, it does the math to say like, well, that should be 3 bytes back. It figures it out for you and writes that in the binary. So that's a basic thing that assemblers should give you so that you're not manually using that quite that way. But that's relative addressing. So you can only store 1 byte offset, so you can go forward or back 128 bytes. If you needed to go to an entirely different place in the code, you don't use branches for that. You might use a branch to test a condition, but then the code that you'll use to wind up going somewhere else is generally a jump or a JSR, right? To completely just change the program counter and go somewhere else. Josh.
Go back to the ROM page. Yeah. Have you talked about the line with the comma in it?
With the comma?
Yeah.
This one?
Yeah.
Oh yeah, I think that might have been right when you ran out of the room.
Okay.
Basically this, if you ever see comma X or comma Y, it's indexed.
Okay.
So that's absolute X. So that's
Okay.
absolute with the X register added on.
So it's saying do that on the X register.
So it's saying start with this number,
Right.
then add whatever's in the X register to it. That's the address.
Oh, okay. Gotcha.
Okay, so good news. Oh, fuck me. This ran off the bottom of the slide. One final tricky bit. Damn. One final tricky bit is that some instructions use the address, but most instructions use the byte stored at the address. So like if the addressing mode, think of an addressing mode as a function that computes an address. Normally, instructions will say, I'm going to use the addressing mode, and it's going to give me an address, and what I want is the byte that's stored at that address. But sometimes they just want the address, like jump or JSR. Jump or JSR just want the address to store it into the program counter. They don't care about what's stored at the address. So there's this little question there. That's a pain in the ass. So all of a sudden, okay, so this is all the terrible things I had to teach you so that we could do the fun stuff. Kind of, I guess, if this is fun. These are all the terrible things I had to teach you. So our model has to change a little from before. Like previously it was like, this one won't be that bad. Like we can just have a class to represent the CPU and its registers, and then we can have methods on the class for the instructions and a big array of numbers to act as memory. But we didn't really have this addressing mode wrinkle. So all of a sudden, not only do we need methods for the addressing modes, so we can compute like what the argument to the instruction is, we need some way to tell the addressing modes whether to use the address or the byte stored there. And now it's not like we're talking about writing 50 methods. We're talking about writing 150 methods, and there's a lot of duplication between them. And that sounds like the worst thing on earth. So we'll talk about how to solve that problem, and that's like the interesting setup. That's the interesting setup, is like you want to write a CPU emulator real bad. It seems like a worthwhile thing to do maybe, but holy crap, that's nasty. Why? I mean, like you're not going to write 154 methods where you're copy pasting half of them like all. I mean, like what do you do? Like that's crazy, right? I don't know. But first, let me take some questions. Ben, and then I think Josh maybe.
So, big array of numbers is memory.
Yeah.
Is that the whole game at the same time?
No, but we're not talking about that today. I will have some notes about that before the end of the lecture.
Like, because it's too big.
Mini games. So Ben asks a question that it's worth just TLDRing right now, which is, what if you wanted to make a game that couldn't fit in 64K of memory? Could the cartridges hold more? And the answer is yeah. Like very quickly, people were like, 64K isn't enough. I want better art. I want better graphics. I want better code. Like I need more than 64K. And Nintendo thought about it for a while, and they said, okay, well, why don't we just make cartridges that have some special hardware inside them that let you swap out chunks of 16K? So you can say, like, you can basically send a write instruction to the cartridge that says, okay, load the next level, more or less. You can say, like, I want to swap out this 16K of data that's currently in 32,000 to 48,000 block of memory with this chunk of data.
So
Stuff like that.
Does your emulator do that?
I do have the memory mappers set up, and yes, my emulator does that. I don't have graphics, so it doesn't matter much yet, but yes, my emulator does that. And that actually wound up not being as bad as I thought. So the biggest design mistake I made the first time around when I was doing the Lisp version of this was that I didn't think through how memory should work. And I just said, you know what? An array of 64,000 numbers will be fine. An array of 64,000 numbers is not fine. And a big part of the reason for that, I'd really love to get into, but I'm going to hold that for in just a minute. But that's a great question. Yeah. And basically they started putting, so that if you have a bunch of Nintendo cartridges at home, the hardware inside them, not the data, the hardware is different between them because some of them probably have swappable like memory mappers and some of them don't. Yeah.
So when you compare the Nintendo to computers on the market at the time, how powerful was the Nintendo?
I don't actually know. That's a very good question. The question was, how powerful was the Nintendo versus computers then? I don't know. I think the biggest thing that probably the Nintendo was probably cheaper than an equivalently powerful computer. The other thing is a lot of the innovation in the Nintendo was actually in the video card, the picture processing unit, which primarily because it had built-in hardware to support scrolling. I'm not kidding. This was a big fucking deal in 1985. It was like, our video card hardware will let you scroll through memory to like literally get tiles like changing as a character walks across the screen. People were like, "Oh my god, I can make so much better games now," and that was a big deal. And that was hardware intensive at the time. Now we could do that in software, and which I will, and no one cares. But then that was like serious stuff, and you needed a dedicated chip to do it. So that was a big deal. The video card stuff was a big deal relative to other things at the time. Yeah, good question. Other questions? All right, it's been 2 hours. I'm going to fly us out of here in the next 15 minutes before my battery dies and I run out of storage for this lecture, which I am recording. Okay, so I'm really enjoying this, though. I hope we can have a follow-up when I get the graphics working. Okay, so the question is like, well, how do most people do this? We can have a class. We can have a bunch of methods on it for the various instructions. We can have something to act as memory and methods for the addressing modes. But like, then how do there are all these different addressing modes, different versions of the instructions, like a lot of duplication. Seems messy. How can you kind of detangle it so that the code you wind up with doesn't suck? Because like, what do most people do? So how do most people do it? Like, not to be rude, I'm not trying to pick on this author, but like here is if you search for JavaScript Nintendo emulator, there are results. I'm not the first person to do this. It seems everyone's written a Nintendo emulator. In terms of hacker street cred, I don't think I'm very high on the list anywhere for doing this, just for the record. But like, okay, so here's the CPU's like run next instruction function inside JSNES. Ready? Okay, emulate a single CPU instruction returning the number of cycles. Well, first we set up some variables, then we check if there was an IRQ, then there's a switch statement to figure out what kind of IRQ and what to do if there was, that's an interrupt, sorry. If there was an interrupt, we got to figure out which one it was and handle it. If it's not, then okay, we need to look up the whatever the next instruction is. This is literally what this is doing is it's pulling whatever's in the program counter out and then looking up what, like it's loading the number from memory that the program counter is pointing to. Then it's looking in an object to see like what method goes with that, what information goes with that. Then it messes with the cycle count. Then it figures out what the address mode is. So it looks at the program counter and does some kind of math. I don't know what's going on here. They're bumping the program counter around. Then they're saying, okay, like based on the address mode of the instruction, which we figured out here, here's a switch statement to do literally the load to get the argument that you need, right? And then here's the really fun part. Okay, once we have the argument, now we can actually do the instruction. And here's a switch statement for all the different instructions. Oh, there we go, right here. Yeah, and there's your CPU. And if it's this, then you use something that's not a legal opcode and like, boom. Because there actually was, technically there are these things called illegal opcodes. Certain numbers were not officially supported, but did things. So it turns out most games did not use the so-called illegal opcodes, though, at least extensively from what I can gather. So I'm not planning to support them. And I don't see many other people that do either. But there is some documentation from crazy hardware people that just had to know what they did, that sort of thing. Anyway, personally, I'm not wild about this code. I understand it. I get the rough structure. But boy, it feels like we took a step back in programming. Does that make sense? Like, this is as well written as it could be for the design choices that were made, I think. But like, definitely, it feels like we stepped back to an earlier time in programming where we didn't have like nice abstractions like functions. In fairness to this author, I expect part of the reason that they did this was because at the time it was written, I don't think JavaScript had classes yet, for one. Two, I don't think it had a module system, so like they've got some global variable that everything basically is getting tacked onto inside unimmediately invoked function expression, right? So kind of classic JavaScript code in that way. But like, not my favorite thing. And then, you know, manually adding things onto the prototype. But it still feels really messy. Also, I think part of the reason they did this was for performance. There may have been a time when browser engines could not be as fast as they should be. Before they had JIT compilers, a switch case might have been the only way to get the performance you needed for this thing to run at 60 frames a second. JavaScript engines have gotten a lot faster in the last decade. In 2005, I sincerely doubt that in 2005 you could have made a Nintendo emulator that ran at full speed on a laptop computer. I don't think you could have done it. Now, sure you can. It's not hard. I've done it. But then it was hard. So that may be part of this. But so like a lot of emulator code is like this. And if you remember, like back to the goals, years and years and ages ago. Whoop. Nope. Hang on. There we go. The goal. If we think back to the goals, programs should be written for people to read. They should be clear descriptions of how things work. They shouldn't just be like, I got it. You know, it runs. That's never been good enough for me personally anyway, at least on hobby projects. When you're at work, sometimes you gotta do that, but that's another thing. So with that in mind, and 90 slides later, what I decided to do is use closures, because closures are fucking amazing. And in any language where you have a closure, you have higher order functions, and you can pass functions around, you have magical powers. You seriously have great stuff at your fingertips. That is such a basic building block in programming and in programming languages, but you can go so far just with that. It's bananas. So, did I not, wait, I have a note to self there, and I should have some links. Hang on, let me check my slides. Did I not recompile this? Where, There we go. Addressing modes, opcodes, init. Okay, save, forgot to save the file. Recompile the slides. Refresh the page. There we go. Sorry, y'all. Okay, so how did I do it? Well, first things first, memory is an object. I'm going to go horse in a minute. First of all, memory is an object, and it looks something like this. You've got this thing called memory. It takes in a mapper, or it's got an actual array somewhere. I don't even know if I use this. Yeah, I do. I had to think about it. Okay, long story short, memory is a thing. This is kind of complicated, and we'll talk about it in a little bit, but memory has a load instruction. And based on what you try to load from, it pulls from different places in the hardware. Because in fact, it turns out that the cartridge got the last 32K of memory of the address space in the original Nintendo, and that was it. The cartridge got the last 32K. The video card, which could talk to the cartridge to pull like art and stuff, got everything between 2,000 and 4,000, which is I think 8K, 16K. I can't remember off the top of my head, but it got a certain region of memory. And then there was a certain region of memory that was for the CPU's actual like RAM. But based on what address you were working with in memory, you weren't necessarily pulling from like one big array. There actually was stuff all over the place in different parts of the hardware that you were talking to. And that was something that the first time around I just had no idea and was like completely unprepared for, right? When I wrote CL6502, I was like, oh, you have a big array of 64,000 bytes and it's fine. And like, it's not fine. That was one reason I had to rewrite. Anyway, where the addressing modes are concerned, there's a lot of stuff like this. Each addressing mode gets past the CPU. It has to have the CPU to be able to do its work. And then it just does some math. And that's what they literally just compute an address and return it. And that's it. That's all they do. And that's all they should do. right? Ideally, that's how they're described. That's what they should do. You might see some of this stuff. I'm still happy to talk about that in a minute. Basically, it's making sure that you don't overflow. So if the start address here was the last byte in memory, and I added X and X was 1, I might go out of 16 bits. I might overflow. This just wraps it around to 0, or wraps it around to 1 or 2 or 3 or what have you. That's how logical, like bitwise AND works. So you'll see that in a lot of places throughout the code. But basically, all of these things, relative is the only one that's complicated because you've got to figure out if it's signed or not, right? So the top bit in the offset's a direction with 1 meaning go back, 0 meaning go forward. Remember, negative numbers are in 2's complement. Here's the Wikipedia page. If I was reading this, I might go like, oh, I think I can figure out how the Nintendo's addressing modes worked. At least a little better. So this is where all the addressing mode code is. These are just methods that are on a memory object. That's it. Those are your addressing modes. There's some other stuff like load and store, and that's the general interface you'll use in a lot of places, but that's the addressing modes are just methods on that object. The opcodes. The opcodes are on the CPU object. The CPU object looks like this. As I said earlier, you got to have registers. So here's the program counter, the stack pointer, the status register, the accumulator, X and Y, with what I glean to be the correct startup values for the hardware when you turned it on. Then you have access to the memory object. You receive an instance of it when you build the CPU, so you have memory. And then finally, there's an opcodes object and an ops info object. The opcodes object literally has a bunch of byte keys, and each one maps to a function or a method for whatever that instruction was, right? The ops info object has things like what was its name, how many cycles did it take, how many bytes were its arguments, those sorts of things. And then finally, there's a cycle count because you probably want to figure out how much time has passed after you've run a couple of instructions.
That was my question.
Questions about that? Yeah, questions about that.
If the cycle count was what you said that the Nintendo didn't do this, but your emulator would.
Yeah, so the Nintendo just actually ran at a certain speed, and that was exactly how fast it ran, and so you don't need a cycle count. If you're writing an emulator, you have to have a cycle count, because otherwise your CPU might be running at like 5 times the correct speed or a third of the correct speed, and you have no way of like really knowing, right? So you need a cycle count to be able to say, to be able to kind of clock yourself and see that you go the correct rate. Yay. Yeah, so that's the thing. And then the way that I set up the CPU is, we've got all these different opcode versions. Let's just take the instructions and make them all methods. And here we've got all the CPU instructions with one thing that I haven't quite done, which is deal with overflow and addition and subtraction, because it's slightly nasty and I just couldn't be bothered at the time. Also, I want to see if it breaks anything. Like any games, I want to see if I try to play Mega Man and it's like, oh no, it just loses its mind because of overflow. Here's addition, right? Here's something simple, every instruction you'll note takes an addressing mode as an argument. So literally all the instructions get past a method that they can use to get whatever data they need. That's it. As long as this thing gets an addressing mode, then it can call it to get the data out of memory that it needs, do whatever work is required, update whatever in the CPU it has to, and then that's it. You run your instruction. Right? So I literally just have all the instructions in here. It wound up being about 300 lines of code, probably 250 or so once you take out like all the helper utility functions I defined at the top and like the class declaration and stuff like that. Not a whole lot. And some of them are like brain dead simple, like transfer the X register into the stack pointer. The stack pointer now equals the X register. Duh. I mean, like it's not that bad if you actually separate out the pieces. What are the pieces? Right?
Set flag ZN.
You want to see set flag? So set flag ZN is incredibly common. I have a general set flag and then set flag ZN. So there's clear flag and set flag, which either set a certain flag in the status register to. I'd love to talk about these specifically, but why don't we hold that for just a minute, Nick? They're like I'm happy to explain any of this, but it could get slightly more involved. But basically, I have ways to either set a flag in the status register or not. Set flag ZN happens in tons of instructions that do math, and it just says if the result was 0, then like set the 0 flag. If the result was negative, then set the negative flag. And so that's just was so common that I just defined a helper for it, and a couple other emulators do too. Okay, so the last question is like, that's great. And this doesn't wind up being that bad if you can break the code up this way and you can pass instructions in addressing mode. That was a big design insight for me the first time around with this, and a big design insight for me, still something that felt very good the second time around. I had to work a little harder to figure out how to do it with JavaScript in some ways, but that wound up being fine. The question though was, where do you specify all that stuff, and what does it look like for the CPU to run an instruction? So first, let's start with that. Here's what it looks like for the CPU to run an instruction. You load whatever is in the program counter, because it should be pointing to a valid instruction. Then you have this opcodes object. You look the instruction up in there. The instruction should be a number, and if you didn't know, yeah, you can totally store numbers in a hash table or in an object. So you literally, and the reason I used an object, you might say, fine, but why not use an array? The reason I used an object instead of an array is because there are a lot of numbers for which there isn't an opcode. Like there are a lot of numbers for which, like I'm guessing here, but 237, there might not be a method that goes with 237. And I don't want to have an array that had like, what do you have in the array if that's the case? Do you have a function that does nothing? Do you have a zero? Like what do you do? I couldn't decide, so I decided let's not do that. Let's literally just have it be an object, and you can look up the keys, and they just happen to be numbers. But anyway, we grab whatever that is, whatever comes back is a function, and you call the function. Ta-da! That's how a fucking computer works, right? Hopefully, something like that. Does anyone spot something weird about this, though? Your brains might be too fried. It's totally fine if you don't.
Well, you say it's an object, but it looks like an index in a array.
Yes, and it is an object, though, and yeah. The weird thing is I'm not passing an argument, and I said a minute ago that every instruction should get an addressing mode.
Oh, yeah. One on there.
So that's really kind of the final trick that let me get this as my step code, which I think is nice to read and pretty clear. So the deal with the step code is I have this set up. I can't directly use these opcodes perfectly the way they are. Like these instruction methods. The reason for that is, for one, they each change the program counter by different amounts. If I run ASL in immediate mode, then it should bump the program counter by 1 to get to the next instruction. If I use it in absolute mode, it should bump the program counter by 2. It also takes a different number of cycles depending on what the addressing mode is, et cetera, right? And I don't want to have to look up what the addressing mode is in the step instruction. I guess I could, and it wouldn't actually be that messy, to be totally honest with you, but it would pollute the clarity, I think, ever so slightly of this, which is very straightforward. So what I decided to do was have this particular, so I have this thing called init opcodes. So if we look in the CPU, the last thing that happens in the instructor, in the constructor, is I run this function called init opcodes, which is defined in another file, that takes in the CPU and takes in the CPU's memory. And what it does, seems a little goofy, I realize. What it does is it literally defines just the variants as arrays of arrays, just data. So like here's an array of all the different add instructions. We've got one which is byte 61, 65, 69. This one takes 2 bytes to store in memory, and it takes 6 cycles to run. And the addressing mode to use is literally the memory method indirectx. This is a method on the memory object right here. Now I'm not running it, right, because I didn't add parentheses at the end, but I'm naming it. I'm saying that method in the memory object is the one I want to use, right? That's the method I need. And so I have all these things defined for each of the opcodes, and then I literally just go through, and on each one I call a function called initOp. And what initOp does, way down at the bottom, is it loops over all the different versions in the array, and it says, well, the op is whatever the number, whatever the opcode actually is at the front. Then it takes some arguments, and that's your version. By the way, this is called destructuring. If you've never seen destructuring in JavaScript before, if you know that this thing is an array, you can actually take it apart like this. There's an MDN article about it. Destructuring is great. More programming languages should have it. Destructuring is great. So Then I say I have a function called buildOp, and I have a function called buildOpInfo. I take the results of those, and I store them into the CPU's opcodes object in the right place, and into the CPU's opsinfo object in the right place. Then I can look those up whenever I need to actually use the function, or to disassemble it, or what have you. The very last thing I have to show about that, so buildOpInfo has the method's name, the addressing mode's name, any documentation, the size and the number of bytes to store it, right, and the number of cycles it takes. The buildOp is the slightly tricky piece that I want to spend just a second on. Basically, I have a bunch of arguments here, so you can say whether or not some instructions, you don't actually want them to mess with the program counter much, like jump. All jump should do is set the program counter to exactly one thing, but you don't want to bump it in any other ways, like you normally would to like go to the next instruction. You just want to set it. So I have this argument here to say that, long story short, I take whatever the method is and build a new function that is what gets stored in the opcodes array and that we wind up using. And the way that works is, most of the time for any instruction you're ever going to run, you want to bump it so that the program counter, once you're in the instruction, is looking at the first argument, or the first thing after the instruction, not the instruction itself. You're not normally interested in looking at the instruction itself in memory and operating on it. So what I do is I just say I'm going to build a function. Each time, the first thing we do when we're running any instruction is we bump the program counter to look at the next thing. The next thing we do is we run the method passing it the addressing mode. This is bananas. This is very tricky, in fact. This is very tricky stuff. Or I'm sorry, we have the method, we bind this to it. I think this is the CPU in that context. Yeah, so we have the method, we bind this to it in that context, which is the CPU. This I do not like JavaScript for, sorry, but that's a thing. So we run the method with this bound to the CPU, passing it the accessor, which is the addressing mode, which we get from something that builds it, because sometimes you want the byte of an address, and sometimes you want the address itself. So we get the accessor, we pass it to the method, the instruction runs. Afterwards, if it's most instructions, not a jump subroutine, then we've got to mess with the program counter. So we want to add however many bytes the instruction takes in memory minus itself, the opcode. So we'll bump the program counter by that many bytes to get to the next instruction. And then we'll update the cycle count in the CPU and return it. And so those are the things that I actually wind up storing in an array or in an object and indexing into, and that my step function runs to make the CPU tick. And it works pretty well. And the code is pretty comprehensible, I think, on the whole. Some of the, you'd have to actually go through all this, but I think this one key insight about that is we're treating this problem of many, many different versions as a data problem. We literally model that with data structures, arrays of arrays. What method to use? Well, that's just data. If that's the only thing that's really changing is what method to use and 2 bytes, model that as data and then make the problem data-driven. And what I'm actually doing here is using higher order functions, like returning functions back, to generate the right code automatically and put it in the places where it needs to go. It's trickier to understand that piece, probably. That's a little bit more intricate than just having a big switch case statement, but it cleans up the rest of the code tremendously on a conceptual level, which I think is worth the trade-off. There's probably an argument to be had there, but I've been, ever since I settled on this design, I've been very happy with that decision. And that, basically, I have a couple of additional slides, not many, but that is the overall design that I settled on. That is how you build a Nintendo emulator, in my opinion, at least for the CPU. Josh.
You go back to code.
Yeah.
Is that a promise?
Where? No. There are no promises in this code because there's nothing asynchronous in this code.
Okay.
Yeah.
So it's not waiting on the result of all that to.
No. This is building a function right away and returning it right here. That is then used in init op to store it into the CPU's opcodes object. Ben.
Are you binding the address mode, or are you only binding the CPU?
I'm binding the CPU. because the method
So-
needs to have, so you get into some troubles with JavaScript because when you're storing closures and using them later, like running them later, the value of this changes. And that's bad for me because all of the instructions refer to the CPU as this. Because it should be a method on the CPU. Like conceptually, an instruction is a method that does something on the CPU. And so that's the way I've written all the code, but I need to bind the CPU because otherwise when I run this thing later after I pull it out of the array, this is undefined. And then I'm really screwed.
So you bind the CPU and the accessor, which is the address mode.
I bind the CPU
is
here.
already in the array.
I bind the CPU here to the function that's being built.
Yeah.
I make sure that the CPU is bound to the method, which is also a function that was passed in from somewhere else here. And I'm passing in the accessor, which I don't do binding on.
But that function with the accessor as the argument is stored in the array.
Yeah. Yeah. Yes.
Okay.
It's a cool trick, I think. Okay. CPUs. Okay, so what didn't we talk about? Kind of a lot, but nothing super important. That's not true. I immediately go to a slide called correctness. I love that. Okay, so how do you know what hardware should do in the first? So like, let's step away from like this technical thing. I'd be happy to answer more questions about the code. It's all up on GitHub, like all that kind of stuff. But let's step back for a second and talk about some of the other things about the design, or like some of the other issues. So one thing you might be wondering if you wanted to undertake something like this, or if you just think I'm crazy, which hopefully you do, is like, how do you actually know that this stuff is correct? Like, what do you do? Do you unit test it? Like, what do you do? One thing is you've got to know what the hardware should do, and the good news is it's 2016. People have taken the NES apart to high hell. There is so much documentation about what the hardware does. It makes it easier. From my vantage point, all that stuff is written with the assumption that you actually were a systems programmer at some point and have spent a lot of time with pointers and like 2's complement. Which was a pain in the ass for me because I hadn't, right? Like I'm trying to learn how hardware works. And so that was a difficult part of the process because while there are a lot of references and they are good and they are precise, they kind of look like math formulas sometimes. You're like, this is exactly what the, bitwise operators you would use are to do something to like this part of memory or how this addressing mode works. And that's fine, except for the fact that I don't actually understand what it says, right? So it took a while to kind of unpack some of those things. But there are a lot of references. There's very good documentation. NestDev Wiki is like, there are people that have been making homebrew software for the Nintendo for a while, and they've got so much knowledge built up. And a lot of that's for the purposes of emulator authors, but there's also a lot of it that's like, hey, do you just want to write a Nintendo game? Like, here's what you should know to get started kind of stuff. So more geared towards the assembly programming side. This lecture has been a little bit more about the hardware implementation. There's also plenty of other source code to refer to, other Nintendo emulators that are out there, but as you saw, that's a mixed bag. I have found some in the last few years that I think are really nicely written. Other people have beat me at the punch here in a lot of ways. There's a guy that wrote one in Go that's beautiful. There's a guy that wrote one in Rust that's pretty good. Quite good, but I think some of the type system stuff gets in the way a little bit. Josh.
Is there any way to open up a ROM and look at code?
Disassembly, yeah. I mean, most of the emulators have some support for like as you're running the ROM, pausing it, and like mine does. Like that's what I'm doing right here. If I step, I'm running an instruction, and you'll note the program counter down here is changing, and the disassembly listing updates. So yes, there are ways to do that, and that actually, I'm going to have another slide.
Like, open it up in Emacs or Sublime.
You can't open it up in Emacs. And in fact, you can't even statically disassemble whole programs. So like that I have this listing that somebody painstakingly created for Super Mario Brothers 1, but you can't even run it through some sort of processor that like does this. You would have to actually simulate how the Nintendo works. Because like some of the data is not loaded into memory at first. It might be in a bank of the memory mapper cartridge. Like it might be not switched in. Also, sometimes you had people that would write assembly that did something called self-modifying code, where you literally have an instruction write to an address that has another instruction to change what it does. So like you cannot statically, you have to run the entire thing basically if you want to figure out how it works. But I think I'll talk more about that in a minute. So okay, then there's the question of like, okay, but how you test it? You can do unit testing. I use a process I like to call blind hope. And long story short, like a lot of the things you would want to unit test are really complicated combinations of instructions, not a single instruction by itself. And like if you look at most of those methods I was describing in the CPU, like they're wildly simple, right? Like most of these methods are things like, you know, branch if the carry flag is not set. Like I'm not curious if this code is correct. Get flag carry does not equal 0, branch if. I'm pretty sure that does what I think it does. You know, like on an instruction level, if you separate the pieces outright, the instructions are brain dead. A lot of the testing problems, a lot of the testing headaches come from how things wire together. So unfortunately, like it doesn't seem prevalent for emulators to have a lot of unit tests. Even nicely written ones. Like I'm not saying that about just like in general, unit tests are not common for emulators. What there are, because the things you'd wind up wanting to test are like if an NMI, which we haven't talked about, an interrupt, it's an interrupt. If an NMI was sent by the video card and then there's an indirect jump done that crosses a page boundary, are these certain bits in the status register set? That might be behavior. That might be behavior that Super Mario Brothers Super just will not work at all if it's not there. But like, good luck finding all the test cases you need. How many combinations of events are there that you would have to check to make sure that all that stuff works? I mean, you'd lose your fucking mind. So nobody writes tests for that by hand. There are lunatics that have written things called test ROMs, which literally are like assembly code that they assembled that you can load into your emulator that will break in a described way. And like maybe it loops the program counter at one exact spot if your code doesn't do X correctly, and it loops the program counter in an exact spot if your code doesn't do Y correctly, and so on. So like test ROMs, very helpful. They do exist. That is a thing. You've then got to read all their documentation to figure out, you know, what the output is telling you, because it varies, but that is a thing. You don't have a command line for the CPU, unfortunately. So finally, the last question is like, well, how do you get this thing to run on the page? In short, in traditional languages, you just use an infinite loop. While true, update, draw, the new screen, whatever, or CPU fetch, CPU load, CPU step, whatever. That doesn't work in JavaScript. In JavaScript, one reason is that you can't actually force the browser to draw. The browser is constantly redrawing the screen, but it decides when to do that, not us. We can change the DOM, and later it will update the screen. We don't have direct control over saying, like, re-render the page. That actually is something that the browser does behind the scenes, as fast as it can, or as fast as it thinks is reasonable, but on its own schedule. So if we say while true like this, we'll actually just hang the event loop. We'll actually just hang the browser tab, which is bad. Also, it would run faster than the Nintendo, quite possibly, right? So we don't want to do that. So we need to slow it down. We need clocks. This also gets into why the graphics isn't done. You need to keep the graphics card, which was concurrent, asynchronous, a separate process, running in time with the CPU almost perfectly. And that is very complicated. We won't get into that today, but that is a very complicated thing. The graphics card needs to be at a very specific place when the CPU is at a very specific place. Basically, you never want the CPU to access the graphics card's memory while it's drawing, which it's doing most of the time. There's 60 frames a second, and there's a very small window in between frames where you can actually have the two talk to each other and not potentially break something. So getting the clocks right is complicated. And that's really what I think the real struggle, once you get the CPU piece figured out, isn't necessarily any of the behavior of the other parts, where it's just like, it's tangly, but it's well specified, but it's making sure that all the stuff is clocked together correctly. That is nasty. So your next thought might be like, okay, we can't do while true, let's just use set interval. But request animation frame is a thing that browsers got in the last 5 or 10 years, and it's way better. It actually tries to sync with the browser's refresh render loop as best as possible and provides the callback that is given with a high resolution timestamp. So what you actually wind up doing, and I can show the code in a minute if anybody wants to see it, is you say, you have some update function that runs the CPU, runs the video, runs the audio, and puts whatever comes back to the screen. And you run that with request animation frame. Every time it gets a timestamp, and you see literally how much time has passed since the last picture you drew or whatever, and compute how many cycles the CPU and the video card should run, and step them that many times. Kind of crazy, but it's it works very simply and pretty well, and I've got that, so that's good. So you can compute the cycles and just run it. In a future lecture, perhaps, we'll talk about memory mappers, so how you swap stuff on and off the cartridges, how the pictures work, how the audio worked, and how to integrate all those pieces. Having gotten through the mess of concepts that we had to get through for this one lecture, I think a second lecture of equal size to this one could probably cover all of that, to be entirely honest. So at least stages 1 through 4. So memory mapping, pictures, audio, and integration. What I'm really excited for on some level is stage N. I have to look at that. So once all that stuff is working, there's still other things I'd like to do with the project. Then this is kind of to Josh's point a little bit earlier. So we won't do the bonus slides, don't worry. Oh. So, recompile. Okay, so there are other cool things you can do. For me personally, the next thing is graphics, then audio. Then there is one, so there are actually a bunch of the different memory mappers that let you swap in and out pages of data in the game. There are like 100 of them. I'm not writing code for all of those. The good news is about 90% or 95% of games that were shipped in North America used one of 5 memory mappers. I've gotten 4 of them down. So there's one left. Unfortunately, it's the one used for Super Mario Bros. 3 and Teenage Mutant Ninja Turtles 2, obvi, so gotta get those done at some point, right? It would be nice to add an assembler to this. That would be cool, because then you could write your own code, load it, run it, just play with it, right? Then finally, the real like crazy person, this could take a decade of my life, and maybe I'll keep messing with it, maybe I won't, scale of things is like, why isn't there, so Josh said, like, can you take apart games while you're playing them? And the answer is there's really not a tool for doing that. There's not a tool for helping you understand how Super Mario Bros. 3 worked, or how Mega Man 2 worked, or something like that. And it's a reasonable question to think, like, well, would that be possible? And I think it is. I think there is, certainly with the emulators, you can watch the graphics data as it's loaded in and out. And you can watch, like you can pause the game at any point and say, disassemble the code right in front of me, things like that. It would not be crazy to add some of that functionality to this. And that would be super cool to do, I think. I don't know how long it would take, but it's in the bounds of possibility, and it's been done before. And it would be in the bounds of possibility to add like an automatic like song playlist generator where you could load in a ROM and it was like, do you want to play any of the sound effects or music? We can't tell you what they are, but like here's all the audio rights we could find. And if you do this, we'll just run that loop and then like you'll have sound. Or like stuff like that. I think it would be reasonable to do some sort of thing like that, and that might be cool or fun. Or just give you something that lets you compose music, kind of, for the Nintendo synth. I don't know. Like there's room to do weird stuff like that. What I'm really interested in on some level, and I think that like literally you could probably get a PhD in this. So maybe at some point I'll go back to school. I don't know. It's very much unexplored territory from my perspective in computing. Is how could you run the code and graph out all the execution pathways as you did, so that instead of saying like, well, I can disassemble this like 10 bytes that I'm looking at right now that I know is an instruction, you could build a control flow graph, what's called a control flow graph of the program, and then maybe you could turn it into a nice language like Python or JavaScript that had an API for doing the things you'd want to do with a Nintendo, instead of like assembly. Maybe you could up-convert stuff, if not into a real programming language or real code, at least into a representation that made more sense, where it goes, you're in this loop for a while, and you can start annotating things and say, when we're in this part of the graph, this is what's happening. When we're in this part of the graph, this is what's happening. And you can kind of zoom out and get a bigger view of how the program actually works. That would be amazing. Nothing like that exists anywhere for any language that I'm aware of. I mean, there are like advanced disassemblers and hex debuggers, but they really don't go that far towards that sort of thing. But that would be an interesting like windmill to waste a lot of years tilting at. Conclusions. And then I'll come back and show Frodo Red Pill for like half a second because this is amazing. And this is the only thing I've seen that kind of comes close, and it's really cute. You too can be a systems programmer or hardware hacker. If I've learned anything, it's that. Like I really like, if y'all wasted as much time on this crap as I did, you could do whatever you wanted, I'm sure. So it takes more time than usual reading documentation. And it takes more time at a whiteboard to make sure that you understand stuff, just to work the math out and go like, okay, I get how 2's complement works or something like that. But after that, like, it's not harder. In fact, in some ways, I think it's easier, right? When you're at low level, there's no framework to be sneaky. There's no like super weird, there's no under the covers stuff to hide like from you. So there's no magic, right? Anything that's happening, you can say, I know exactly what happens next. If you can look at the state of the processor and you see the next instruction, you know what's going to happen. Like, most of that stuff is very sneaky, or is very clear. Your brain knows the answer, you just have to work it out. Some things are harder, though. Specifically, a lot of the stuff we're used to debugging-wise just doesn't work, and it's a real monster when stuff is like half implemented and mostly working, but there's a small bug, because then you know what the CPU should do, but not necessarily why it did what it's doing or what have you. And how to test, as mentioned previously, is like, who knows, man? It's a mess. Test ROMs are the answer. Finally, there are a couple of good resources that I've really enjoyed. There's a book from MIT Press that comes out of a site of their publishing house called Platform Studies. They also have one for the Atari. This thing's amazing. It's about 200 pages. It's much more, it is trying to figure out, like, it's not a text, it is a textbook, but it's not a CS textbook. It's not a lot of code and math and diagrams. It's a story about how the Nintendo was built, from the perspective of hardware designers, from the perspective of like business people in Japan, from the perspective of like all that stuff, how games came to exist for it, and what some of the technical constraints that we've talked about today had to do with that. How those technical constraints about scrolling or about memory access fed into the games that actually wound up getting made and things like that. It's a very interesting book, very, very well written, about 200 pages, and it's cool. So that came out from MIT Press. This is kind of a huge motivator for the project that helped me initially get started on it. So as of 2007, there were still parts of the CPU that people didn't know why they worked the way they did, or weren't 100% sure of what the correct behavior in an emulator should be. Like, after a decade and a half of study, they were still like, I don't know. So some people got really crazy. They got the original chips. They used sulfuric acid to burn off the top of the die that covers the circuitry. They got microscopes. They then put it all into a graphics editor. And basically, they did all this insane research to literally be able to simulate not the behavior, but the hardware, an actual transistor-level simulation of the 6502 processor. They gave a talk about it. The talk's amazing. The product is a thing that they wrote in JavaScript called 6502. It runs a lot slower than mine. It runs about 1,000 times slower than the actual chip did in 1980 whatever. But the cool part is you can actually, where is it? Yep. No, where's the simulator? Simulate. There we go. Visual Sims. Hang on. So they actually have an emulator, assembler, and disassembler, and you can actually run the CPU and see literally what the chip did and pause it at any time and examine states that we previously had no way to like access or figure out what was happening. So this is one of the most bananas things I've ever seen. We're like, to be clear, to reiterate, we're not simulating what the hardware did on a behavioral level here. We're simulating physics well enough that it just does exactly what the hardware did. There is no possibility that this deviates in any way from what the actual chip did, because we're simulating physics. We're running a physical simulation, not a like behavior-based one, which is insane and great. What's that? I don't know. I don't think so. It's bananas. Like this guy, Michael Steil, gave a talk about it at a conference in Germany like a year or two ago. It was only 3,000 transistors. It was a really small chip. I said 15,000 earlier. I was way off. It's like a 40-minute talk, really. It's not 60 minutes. If you enjoyed any of this and you're just curious, watch the first 10 minutes. If you're not entertained, turn it off. But you might just be like, are you for real right now? Like, it's crazy. It's super crazy. So I love that lecture. And that was one of the things that, like, in 2011, I watched that and I was like, you've got to be kidding. Like, screw it. I'm going to try to understand some of this stuff more. And that's Visual 6502, and that's the lecture about it. There is a thing called Easy 6502 by Skilltrick if you want to try like reading and writing some assembly code, and they walk you through in much more detail than I did how to write assembly code, and even have like some stuff wired up for like if you write to certain addresses, you can do Snake. They have a Snake game somewhere on here. So like you can assemble it and run it. Wait, I'm not lying. And they've got a debugger and stuff like that. What's going on here? Oh, that's not loaded in completely. That is not the complete program for Snake. See that? That's not Snake. Anyway, they have, what about this one? There we go. So they've got like a little Snake game that you can run in the browser, and it's being run in the emulator, and you can play with that and try and actually get more of a feel for like how that stuff could work. So EG6502 is cool if you want to dig a little deeper. Finally, this guy did try to do kind of what Josh said and like statically recompile a Nintendo game to just x86 rather than emulating it, like figure out the right code to generate ahead of time to just completely port it, and found that didn't work for some of the reasons discussed before. Chunks of code are swapped in and out. Chunks of code could be rewritten while the game is running. There are too many weird, tricky things to simulate timing-wise. Like, just don't try it. It's really hard. This is a long article about that. It's actually very long. Very, 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 very long article. But that's a cool thing. And then finally, I linked to the NES Dev Wiki because I spent a lot of time, there going through their documentation on different things, and it's quite good. Last thing, you knew I couldn't do a lecture in less than 3 hours, right? I think emulators could be cooler. I think simulating basic hardware has a lot of possibilities to like teach us about how programs work and how computers work in a way that has been forgotten now because we just don't care about having environments that let us really inspect things while they run. You look at code, and if you can't figure out the code, then you don't know how it works, and I think that's stupid. I think we can build better tools. I think we should. I think we have really kind of a responsibility too, so that programming becomes accessible to more people. No one's really like there are some people that agree with that, but most of the work is happening on the programming languages side, and is pretty academic in nature at this point, because our systems have gotten too big, and industry is like, well, it's never going to happen. Like we've gotten pretty far away from trying to figure out how to represent or make code in a better way on a low level, on a fundamental level. That being said, there are some folks that created an emulator for the Commodore 64 called Frodo Red Pill. It never got finished and like shipped out from what I can tell. Like it's not actively being worked on anymore or anything like that. But long story short, they actually had a zoomable interface that could let you look at memory, and you could load a game up and see it. That's actually a game being loaded in. And then once the levels start going, they add cheesy music so that you know you're in the Matrix. They're about to reveal. If you zoom in far enough, you get the hex. And you can, based on colors, see what's a read versus what's a write versus what's something else. If you zoom in enough, you get the address, whether it's an instruction or not, what the instruction is, if it's an argument. And the blinking is what's actually being done as it happens. This, I do not think you could do in JavaScript right now. You need multiple cores for this and probably C. Like as they scroll, you can see that certain regions of memory are read faster or like move along with the screen moving. They've got stuff so that if you click memory, you can actually edit it. So like you can bump levels or bump like there's some count that if you bump it, it resets, and like you can actually start editing memory values and just see what the game does, right? Things like that. So like this is bananas, and I think you should be able to make a Nintendo emulator that does this, and I think it would be fun for programmers, I guess. So you can skip levels apparently by bumping this address in memory. That says go to the next level because you won. So, and it wraps around when you get to the end of the byte or something. There's all kinds of stuff. They've got tools in there for exploring. Whoop, my computer's about to die. They've got tools in there for exploring the graphics data and like stuff like that, and it's cool, right? I'm a big fan of the idea. I'm a big fan of the idea that that's the thing that we should be able to do and should have access to. So I'm going to stop recording now.